Hello friends, hope you are having a fantastic day today. Now, I know that preparing for a technical interview in itself is a daunting task. Not only you have to study really hard for different data structures and algorithm, but that too is not actually sufficient. Many times on top of learning these things, you also need to know that what type of coding pattern you are going to use in your actual solution. And there are so many options to choose from. So that's why it becomes quite difficult for anyone, even with the proper knowledge of data structure and algorithm, on where to start and what coding pattern to pick up. And picking one over the other can actually determine that how important or how optimal your code is going to be, which is exactly what any FAANG company or non-FAANG company is looking for. So this is going to be a course describing the most popular coding patterns that you can expect in your technical interviews. Knowing these, you would be able to identify that depending on the problem, which coding pattern to use, what type of data structure it's going to use, and that is going to save your time quite a lot in the actual interview. So the purpose of this video is to help you gain expertise amongst all of these coding patterns, and I hope you find it useful, and good luck with all of your interviews. Thank you. Let's learn sliding window technique. This is a really powerful tool that is used in computational, and this is a very popular coding pattern that has been asked in probably like hundreds of interview, thousands or if not hundreds of thousands of times. So this is a really important to learn. This can improve your code and your coding efficiency significantly, and also helps you reach to the optimal solution in the fastest manner. Now, question is, what is sliding window? Before we go into the technical aspect of it, let's try to understand a real life example. Suppose we are given a chain. Now this is an iron chain, and we found out that this iron chain is currently rusting. One way to solve this issue is to use paint on our iron chain. So if we want to paint the iron chain, what are some of the options we have? Well, let's first consider one very inefficient approach, and that is to lay the entire chain flat on a table, and then we start pouring our paint from top on all aspects of the chain. What would happen is that eventually our chain would get converted into the paint, this paint blue, and we would have our chain like this. This is successful. This is what we wanted. But in the process, we would have spilled out a lot of paint on the table as well. And that is not what we want. So what is one better approach to do it? And you must be thinking that, hey, this is pretty simple. We can just use a simple brush, and on top of the brush, we can use our paint. And then using our brush, we would start painting the portions of the chain one at a time. Then again, we would replenish our brush, and then we would keep on repeating the same process until our entire chain is covered with the paint. In this example, what we did is that we took a certain window, in this case a brush, and that size of the window we applied to our input, which is our chain, and then we were able to accomplish our task. Then again we repeated the same process for the next set of window, and again we repeated the process for the next set of window. This is the whole meat of the sliding window technique, where we take a smaller bunch, we apply some computation to that, and then we keep on repeating the same process for the entirety of the input. And congratulations, you just learned the sliding window technique. There is nothing more than that. But there are few technical aspects, and you have to identify in an interview that when to use it and what are the scenarios that you need to consider. Because your interviewer is not going to say that, hey, this is the array problem and solve it using sliding window technique. He is just going to say that this is the problem, what should be the approach that would come to your mind. So in that scenario, one approach I always consider is that to identify when to use sliding window. Well, one most common thing we understood is that the input size remains fixed. There is no changing in the continuously enlarging input size, which means we have a fixed set of input where we need to do some computation using our paint or our window in this case. So the idea is that typically this is a very good candidate for array or a linked list kind of a problem, and even sometimes for the strings we can apply the sliding window logic. How in the strings? Because remember, string is also a set of characters that are just bunched up together, and that forms a string. So again, for all of these three things, whenever you encounter any problem, you can try to see if it can be solved using sliding window. Now let's just go through the practical aspect of sliding window. What are some of the possibilities we can have in a sliding window problem? First possibility is that suppose we are given an input that is of length 7 currently, okay, and for this one One way we can use sliding window is we create a window of size k. So in this case, let's say for an example, our k is equal to 2 and the window is of size 2. Then we do some computation in this part. Then we incrementally keep on going for the next element. So in this case, since we already took care of this window, now we are going to move on to the next window where we are not considering this element number 0. So for the next window, we are going to go for these two values. For the subsequent window, we are going to go with these two values, and we keep on repeating this process until we reach to the end of our computational input. And this is how we would be asked to calculate some value inside our input and then come up with the answer. Okay, this is one way sliding window can be used. You will need to use 2 pointers that will keep track of the starting and ending portion of our sliding window. And this is going to be the key portion in any sliding window problem. Whenever you can see that the problem can be solved using 2 pointers, then 2 pointer is very closely allied with the sliding window concept. 2 pointer is like Walter White, and sliding window is like Jesse Pinkman. Okay, so that makes things more understandable. Now let's just try to see one example where we will try to solve our problem, and I'll be showing you both the ways. I'll be showing you the brute force way, and then I will be showing you that how using sliding window we can improve upon in our given answer. So suppose this is the input we are given. We need to find a pair of 2 consecutive elements that sums the maximum. So what is the simplest way to solve this problem? If we try to think about the brute force approach, well, the simplest way to solve this problem is to make every single possible pair and then try to do sum of that pair and try to find the answer for that. So that is like pretty simple approach, and we can consider that how it would work. What we would do basically is that first we would take this window. Okay, so this one, the sum currently for this one is 19. Then again we would take this next window and the current sum is going to be 21, and then we would take this window and the sum is going to be 18, and so on and so forth. Every single time we would be able to do this, and we would be able to find the solution. Now in order to generate the solution, what happened is that for every single value we need to iterate over all the k values inside our given array, because currently we are being asked to give us the pair of consecutive elements, so 2 consecutive back-to-back elements. In this case, the time complexity is going to be that we will have to iterate over every single element at once, so big O of n multiply by big k. So in this case, since k is equal to 2, it is going to be big O of 2k. So this is going to be the time complexity for our problem if we use the brute force approach, because for every single time we will have to create a new pair, do its sum, and then get that value considered. In the next approach, the idea is that rather than this, if we use a sliding window, our lives would be much more easier, and we would be able to solve this problem in big O of n time only rather than big O of kn. And let me show you how. The idea is that first of all we are going to create 2 pointers, and for these 2 pointers we are going to have a starting value and an ending value that is true. So first time the starting value is going to be at the first position, so value number 0, and our ending value is going to be at value number 1. Okay, now what we are going to do is we are going to do the sum of these 2 values. So currently the sum of window is going to be 19. Okay, we are at the same time also going to have a max variable where we are going to keep track of that what is the maximum sum we have found so far. So initially this max value is going to be like the lowest value possible, and if we encounter that for any given sliding window the sum is greater than what we have, we would add that value to our maximum variable. So in this case currently the maximum window sum we have found is 19. Okay, now we need to check other sliding windows. So what we are going to do is we are going to do like start plus plus and end plus plus. So our starting and ending pointer is going to be updated. So now this is going to be our new starting and new ending pointer. So again the value is 18 and 3, but this time we do not need to calculate the sum of both of these value to generate our sum. What we can simply do is we can take the previous sliding window that we have calculated, and then what we did is we got rid of this element and we added this element. So this is simply we can apply to our sliding window as well, where from our existing sliding window 19, what we can do is we can get rid of value number 1, so the previous starting value, and we can add the new ending value, so plus 3. And if we do this, we will basically get our maximum sum to be 21. And in this case, since 21 is definitely greater than our input, our max sum, so we will get rid of this one and we will add the maximum sliding window sum we have found so far is 21. And currently the sliding window sum at this moment is also 21. Again, if we repeat the same process and we get rid of this 18 and we include this 15, then again we need to do 21 minus 18 plus 15, so that would give us the sum of value number 18. Now currently you would find that since I'm only considering 2 elements, this would not look much of an improvement. Why? Because you can clearly argue that hey, it's pretty easy to calculate sum of 2 values inside any window. But intentionally I chose the initial window to be of size 2, because say for an example, rather than the input being of size 2, or we need to find consecutive pair of elements. Say for an example, this input is comprised of almost 100 elements, okay? And at the same time we need to return the 4 or let's say 10 consecutive elements that provide the maximum sum. In this case, sliding window approach is going to be a humongous improvement. Why? Because for the first time you would calculate the sum of the first 10 elements, and then every single time you will need to calculate the sum of the next sliding window. You will not need to do the entire computation of all the 10 elements. You can simply apply this formula where you would get rid of the first element, that is no longer be the part of the consecutive sliding window, and then you can only add the next element, and that would be pretty significant improvement in your code. So this is what any employer or any interviewer is going to need to check, and this is the whole core logic behind sliding window technique. Now let me give you a very quick example of an actual real life lead code problem that has been asked in probably, I don't know, tens or hundreds of companies, and we'll see that how we are able to improve upon the solution using sliding window. Okay, so as an example, we are trying to solve the contains duplicate 2 problem. Now this is a very popular lead code problem that has been asked in some of the popular companies like Amazon, Facebook, Adobe, Microsoft, Uber, Google, Bloomberg, Airbnb, and Plenty. So these are all tech giant companies who love asking this question, so that is why I considered this one. Let's try to see the problem statement. The problem statement is actually quite simple, and this is a lead code easy problem and also a very well-liked problem on lead code. Basically, we are given an integer array called nums, or we are going to denote it as n, that contains array values. We are also given a value k, and k can be anything like 1, 2, 3, 4, any single integer value. So suppose k is equal to 3. Now we need to return true if there are 2 possibilities. The first possibility is there exist any 2 values I and j that are exactly same. So if there exist 2 duplicate values in the array, and the second portion is that the difference between I and j, so I and j refers to the index positions of every single value inside the given array. So the index position should be actually less than the value of k. Let's try to understand this with few examples. So suppose our given input n is equal to 1, 2, 3, 1, 5. If this is the input we are given, and we are given the k value to be 4. If this is the case, does it satisfies these 2 properties? So first let's see. Okay, so we need to check that between the window 4 there needs to be 2 duplicate values. Currently we can see that there exists a duplicate value 1 and 1 over here. Let's see the index position, 0 and 3. So if we do the difference 0 minus 3, so basically we need to do the absolute difference, so the answer is going to be 3. 3 is actually less than the value of 4, which means this one currently contains the duplicate value that is not far away from 4 elements from each other. So in this case we are going to return true. Let's try to understand it with one more example. Suppose our given n is equal to 1, 2, 3, 1, 0, something like this, and our given k value is equal to 2. If this is the case, again same scenario, we have the values located at index position 0 and index position 3 that contains the same value, but current k value is equal to 2. And if we do the difference between these 2 values, the current difference between indices is 3. Meanwhile our given k is equal to 2, which means in this case we need to return false, because there does not exist any 2 duplicated values that are 2 steps away from each other or between 2 elements of each other. So this is the whole ask. Now let's see that what is going to be the simplest approach we can take. Okay, so suppose this is the input we are given. Now let's see the brute force way to solve this problem, that we pick any element, then we check the next k elements. So in this case, currently we are allowed to check up until this point. So between these portions, we check that whether 0 is present in any other value or not. If 0 is not present, we can define that 0 would not be a duplicated entry in any of the window, because we are strictly told that we can only check next 3 elements. So in this case, we can get rid of 0 because 0 is not present. Same way, we are going to check for value number 5. So currently value number 5 is located at index number 1, which means we have the ability to compare between these portions. So again, for value number 5, we are going to check this value, and this value, and bingo, we find value number 5. So we can return true in this case because element number 5 exists and the difference is less than 3. But this is like a very inefficient approach. Why inefficient approach? Say for an example, this entry does not contain any duplicated values and all the values are unique, and at the same time what we would do is, for every single element we would compare it with the next 3 elements, and we would keep on repeating the same process until we reach to the end of our loop. And that would be an inefficient approach because the time complexity would be big O of n. So n is the total number of elements multiplied by k, and this is not what we want. We want something more efficient. So let's see a more efficient and better approach. A better approach is that we know that for any single value, we need to check in the remaining portion whether that value is present or not. So currently we can break it down in this sequence. So currently we can create a window like this, 0 and then 5 2 7. Currently we are at this position number 0. Now we need to check that whether 0 exists in the remaining 3 entries or not. First approach is to do binary search. So for binary search, what we would need to do is we would need to sort this given input. And if we sort this input array, the sorted result is going to look like this: 0, 2, 5, and 7. And then all we need to do is check any 2 consecutive values. If we identify that there exists like a back-to-back entries that contains the same value, then we can return true. If it does not contain, then we can move on to the next window. And again, in the same way, we would repeat the same process for this next window that is currently comprised of the values 5, 2, 7, and 3. And again, okay, so let me fix this one. So this one should be 5, not 7, and 5, 2, 5, 3. So again, if we sort this window in this case, the answer we are going to get is 2, 3, 5, 5, and we found 2 back-to-back values that contains the same value. So in this case, we can return true. But the thing is, even this approach is also not very efficient because if we see time complexity in this case, the time complexity is going to be big O of n, then log of k. Why log of k? Because for any given input, we will actually have to sort this, and sorting it cost us a lot of time and energy. And this is better than the brute force approach, but still there can be improvements made. So what is one improvement we can make? And again, remember, we are using sliding window because we know that we need to do this in any subsequent values and we need to find the answer. So definitely you understand by seeing the problem that why we need to use the sliding window. But let's see that what would be the improvement we can make. First thing we need to check is that in the binary search approach, what we had to do is we need to check that whether in the remaining portion does the same element exist or not. And also at the same time, we were considering that every single time we need to create a new window, we would have to do the entire sorting calculation again. So we need a data structure that can very quickly like get rid of elements and add new elements, at the same time very quickly search that whether the existing element exists or not. And the wonderful answer for this type of scenario is a hash map. So we can create like a hash map or a hash set inside our input, and hash map and hash set are wonderful at doing 2 things, like doing the search and remove and input operations in big O of one time. So hashing is really good in that. Also at the same time, it does not allow duplicate entries. So no duplication is allowed, which means we can identify duplicate entries very quickly, very efficiently in any sort of hashing input. So we are going to use this property combined with sliding window approach to solve this problem in the most efficient manner. Let me quickly show you. So first we are given the value of k, which means we are going to create our window. So currently let's just create a window of size k. Okay, so starting from value number 0 to value number 5, and then we will have all the values 0, 5, 2, and okay, let me just put down some different value over here, and let me put 5 over here. Okay, and then this is going to be 4. Okay, so this is these are the current values at the moment. We are going to initialize a hash map. Now inside this hash map we are going to store two items. We are going to store the value as the key, and we are going to store the indices based on its value inside the hash map. So first we are going to check, okay, this one is value number 0, and currently the index values are 0, 1, 2, 3. So 0 is not present in the hash map. We will add entry 0 over here, and its index value 0 as well. Again 5 is also not present, so we will add entry 5 over here, and its index value 1 over here. 2 is also not present, so 2 and 2. And again 4 is not present, so 4 and the index value is 3. So we add these 4 entries in our hash map. At the same time we can check that currently, since the value of k is equal to 3, we already added 4 elements, and still we were not able to find any duplicate entries, which means we will have to update our window. So in order to update our window, rather than getting rid of all the items, what we can do is we can just get rid of the first element, and then we can just shift our window to include one more entry inside our input, and that is going to be value number 5 for the index value position number 4. So again we add 5 over here. At the same time, since we got rid of the first index value, we are going to also get rid of that inside our hash map. So we are going to get rid of the first entry, and currently we have 3 entries. Again we will try to check that whether 5 exists or not. So we will try to input 5 inside our hash map, but we would be able to immediately find that 5 is already present as a value inside our hash map, and immediately we can return true, saying that this contains duplicate inside a k window. And see, what we did is that initially our window was consisting of this value number 0. We got rid of the only 0th value. We kept the remaining values inside our window, and we simply added a new value inside our hash map, and then we were able to immediately identify that whether this is the correct response or not. And say for an example, if somehow this value is not value number 5, this is value number 11 or something else, this does not contain any duplicate entries, what would happen is that every single time we would get rid of the last element from our hash map, and we would keep on adding new values to our window, and eventually we would reach to the end of our input, and if we don't find any answer, we can simply return false in this case. So if we see time complexity in this scenario, the time complexity is actually going to be big O of n only, and since for this case we had to use a hash map of size k, the space complexity is going to be big O of k. But this is a very wonderful and beautiful approach to solve this problem. So that is why the sliding window technique is really powerful, because you are already building your solution upon the already calculated computed values. You are not doing everything from scratch, and that is very powerful in making your inputs more efficient. Okay, so for this problem, I'm not going to write the entire code. I'm just going to give you the explanation. So first we are going to initialize our hash set, and I mentioned that we can use hash map or hash set, anything. In this case, we are using hash set. Now we are going to iterate over the given input array using a for loop. First thing we are going to do is to check that whether our set contains the current value, current ith position of value we are at. If that is the case, we can return true immediately. If that is not the case, we would add that entry to our hash set. At the same time, we would check that if the current size of hash set, if that is greater than our given input k, if that is the case, then we need to remove the earliest entry inside our hash map, and we can calculate that using the number of ith index that we are currently at minus the value k. And then if we remove that value from the hash set, our hash set is only going to contain only the k elements, and then we can keep on repeating the same process until the very end. If we haven't returned true by then, we can return false in the end, and this is going to be the whole solution. Let's try to run this code. Seems like our solution is working as expected. Let's submit this code. and our code runs decently efficiently compared to a lot of other solution. And I would be posting this in the comments so you can check it out from there. Hello friends, hope you are having a fantastic day today. In this video, we are going to learn a very important coding pattern called two pointers. This is a really powerful technique in any coder's hand, and if used correctly, this can improve your code significantly. Not only that, this technique has been really popular on many technical interviews, and all big and small companies, they love asking these kind of questions, because immediately if you use two pointers, you can bring the time complexity from big O of n square down to big O of n, which is a significant improvement. And in this video, I'm going to show you that how two pointer technique works, how to identify it, on what kind of data structures it is being used, and I'm going to give you 3 different examples of actual LeetCode problems that has been asked by, like, I don't know, hundreds of companies. So stay tuned, and first let's get started with what a two pointer technique is. So the most basic definition of a two pointer is that it is a way for us to iterate over any given array or any given linked list. In either kind of a fixed data structure, if we use two pointers, this would be greatly helpful for us to traverse over the given input. Now, there can be multiple ways we can input over the given array. So one way is that our starting pointer is located at the beginning of our array, and our second ending pointer is located at the end of our array. Now what would happen is that maybe after every single iteration, it could be possible that both our starting and ending pointer keep moving towards each other, or it is also possible that in one iteration only the starting pointer moves to the next element, on the second iteration the ending pointing moves towards the other way. And there can be many considerations we can keep on whether the traversing direction sets or not. Now the traversing ends when the starting and ending pointers are about to cross each other. When that happens, then we can conclude that now the traversal of the array is done, and whatever the answer we have calculated, we can return that as the answer. So this is one way to use two pointers. Second way to use two pointers is that we have a starting pointer and we have an ending pointer, maybe located few steps ahead of the original starting pointer, and sequentially we keep on moving from one step to the other step depending on the input. So this is also another way to use two pointers. Now as I mentioned earlier, two pointers is typically used with array and linked list, but sometimes you can also use it with strings as well, because strings is also a set of different characters and that are just bunched up together. So these are the 3 data structures where typically you would consider using two pointers. Also, one more thing, sliding window and two pointers, they go hand in hand, because both of them typically allows you to iterate over the given input arrays, linked list or string in some way or shape, and combination of both of them is going to be very crucial in many coding problems that you will see. So I hope this explanation makes sense. When we move on to the examples, things would become much more clear on how we are implementing the two pointers technique. So the first example we are going to see is going to be the 2 sum 2 problem. This is a really popular problem on LeetCode. This is an additional variant of the original LeetCode number 1 problem, the 2 sum problem. And how it is different? It is different in a manner that given input array is sorted in this case. Now, if you want, you can go ahead and read out this whole statement, but I'm just going to explain you that what the problem is giving us and what the problem is asking us to do. Basically, first of all, we are given an input array that is sorted. So that is great for us. Now we are also given a target value, and our ask is to find that whether there are any pair that exist that sums up and whose sum becomes this target value. If that is the case, we need to return their index values. Now, as a part of added complexity, typically array index values start from 0, 1, 2, 3, something like that. But in this case, we are being told that we need to use one index array. Hence, you see the value starting from 1. So this is just a minor thing, not a big deal. This is very easily done. Now, the next thing we are being asked to do is that we need to find the solution for this problem without using any extra space, which means space complexity has to be big O of 1. This is a really big ask, and this is going to make a lot of things very interesting. So first, let's see that what could be the different ways to solve this problem. Well, first idea that comes to our mind is a brute force approach. And what we can do in a brute force approach is that we take the first element, we consider that can this first element be part of the target value that makes this value number 11. If that is the case, what is the value we need to see? We need to find value number 9. So what we are going to do is, for this value number 2, we will check in the entire array to see whether value number 9 exists or not. Once we identify that value number 9 does not exist, we are going to move on to the next value. Now we are at value number 3. If we are at value number 3, which means for target we need to have value number 8 present somewhere. So again, we will check that whether value number 8 exists or not. Lucky for us, in this case, we found out that value number 8 is exactly here. And the moment we find out, we need to return the index values of both of them. So we can return the value as 2 and 5 in this case. This is the answer. So brute force solution gives us the desired answer, but the thing is the cost is pretty high. Why? Because for every single element, we are essentially iterating over all the other remaining elements to get the answer, and that puts the time complexity to big O of n square. That is a very bad time complexity, and we have to aspire to do something better. So let's see what could be the better approach. Well, one approach comes to our mind is that since this given array is already sorted, why don't we use the benefit from this sorted property? And what is the benefit from this sorted property is that we can actually use binary search in this case to identify any single value. This is a huge improvement. How? What we are going to do is, again, same as brute force, we are using the same approach. So first, if we consider that if this 2 has to be part of the solution, then there must be a 9 existing in the remaining array, because we are told that the target value is 11. So we need to check that whether in the remaining array does value number 9 exist or not, because first value we are considering is value number 2. This we can do very easily using binary search, and we can complete this whole task in basically log n time, nothing more than that. And this is a huge improvement. Now if we keep on applying the same logic, what would happen is that first for this value number 2, we would identify that okay, 9 does not exist in log n time. Now again for this value, we will try to see that whether 8 exists or not. Since 8 already exists, we would be able to return the solution pretty quickly, and basically we would be able to do the whole thing in terms of time complexity. Everything would be done in n log n time, because n is like the number of elements that are given over here, and log n is to do binary search on the remaining part of the sorted array. So this is also a very good approach, but there exists a better approach than this. So let me first quickly show you that why two-sum solution won't work here. Because original two-sum solution we were using a hash map, and in the hash map we were storing the values that we have already iterated over, and then it became really easy for us to find the target value. But in this case we are explicitly told that we need to find the solution using only constant space. So space complexity has to be big O of 1, hence we should not consider using the exact solution from two-sum problem. So now let's come back to our main issue, and let's just find the most beautiful thing, that is the two-pointer concept. What we are going to do is we are going to have a starting pointer at the beginning, we are going to have an ending pointer at the end. Now we know what we are trying to do is there can be three possibilities. First possibility is that if we do sum of both of these values, the sum could be greater than the target value. That is one possibility. Second possibility is that sum could be less than target value, and third possibility is that sum is exactly equal to the target value. The moment we identify that the sum is exactly equal to the target value, awesome, bingo, we have achieved our thing that we wanted to do. But if in any case we identify that whether the sum is greater than our actual target sum, if that is the case, what we need to do is we will need to bring the overall sum down, and for that we are going to iterate our ending pointer on the left side, because that way the overall sum would come down, because all the left values from this end pointer are guaranteed to be lesser than whatever value we have over here because of the sorted property. So this is a huge thing we need to consider. Same way in this scenario, if we identify that given input is actually less than whatever the target sum is, then we need to update our start pointer to move one step towards right, because that is how we would be able to increase our sum of the starting and ending indices, and it would bring us closer to the target value. And the moment we reach to the equal phase, we can return the answer immediately. So let's see this in action. First, if we check, okay, starting and ending pointer, If we do the sum of these two values, it's going to be 12 plus 2. So the sum is going to be 14. 14 is actually too high. Since 14 is too high, we will have to move one step towards left. So again, now we are going to be at the position number 6 or index number 6, where the value is 10. If we again do the sum is going to be 2 plus 10. It is going to be 12. 12 is still greater than value number 11. So again, we are going to move our end pointer. So now our end pointer is located at this position after 2 iterations. If we do the sum, it's 8 and 2. So 8 plus 2 is actually 10. Now we are in this less than scenario. So because of that, we will have to update our starting pointer. So now our starting pointer would be located at this position number 2 or value number 3. And now if we do the sum, 8 plus 3, we are going to get the value as 11, which is exactly what we wanted. So in this case, since we find the answer, the index positions of starting and ending pointer, we can return them as the answer, and the answer in this case is going to be 2 and 5. And this is a wonderful way to solve this problem. Now if we see time and space complexity, in this case the time complexity is actually going to be big O of n, which is the best time complexity of all the approaches I have shown you. And space complexity, well, apart from using couple of variables to store as pointers, we are not using any space complexity. So this is going to be constant space. This is a huge improvement compared to all our brute force approach or our binary search approach. And this is what actually shows you the power of using 2 pointers to iterate over the given input. Now you see, we were using array, and we identify that at any given position we will have to do comparisons between two values. And since the property was sorted, it makes sense that either we are going to move in one direction from left to right, or we are going to move in the other direction from right to left. And here 2 pointer makes a good sense to use. Let's move on to the next example. Now for the next example, we are going to use one of the most popular problems on LeetCode. This is the problem called container with most water. If you see, this has been liked almost 23,000 times. So this is a hugely popular problem, and this is a LeetCode medium problem. So if you want, again, you can read this whole given input, but I'm going to skip that, and I'm just going to explain you using the example. So basically we are given an input array. Now this is not sorted or anything. There is no such property as that. But what we are told is that any single value inside this given array represents the height of that particular element, or a building, or a bucket. You can call it whatever you want to. Now what we can do is, based on the height difference, we can create some common places. So if we consider this value number 1 and value number 2, based on this we can see that we can actually make a bucket that looks like this. Now we cannot make a bucket that looks like this. Why? Because the height of the smaller item is only 1. So this is the only bucket we can make using these two items. Now we are already told that this is already one edge of a bucket. So there is no way that water is going to leak from here. There is no way that water is going to leak from all of these places as well. And we can only fill water up until the point where the smaller edge is located, not the higher edge. Same way, if we want to consider a bucket between this value number 1 and 3, the biggest bucket we can make is going to be of size this one. And this is a way for us to store water in our container. So basically this becomes our container. Now the idea is that we need to find a way to store the maximum amount of water in liters in our container. Now how can we find a maximum amount of water? Basically we need to find a maximum container that can be made. Now the shape of the container is definitely going to be a rectangle in this case, because of the positioning of all the edges. Since it is going to be the rectangle, basically we need to find the maximum area rectangle from these given graphs. And the rectangle, we can only consider the smaller height to be consideration in order to make a rectangle, or calculate that how much water is present at any given position. So the idea in this problem is that we need to find that where we can store maximum amount of water, which means that where we can find the biggest container, or that is of rectangle shape. Now what is the area formula for a rectangle? The area is pretty simple. It's going to be length multiplied by height. Now in this case we have a way to calculate the length, and that is through these index values of this given input array. So this indicates that what would be the length between any two indices. And at the same time, for height, we are already given the values. But when we are considering the height between any two places, we are going to consider the smaller height to be considered as the edge for our container. Now, I hope this explanation makes sense and our purpose also makes sense. So in this case, if we see the maximum water we can carry is going to be between this bucket, because if we see the area of this particular bucket, that is going to be the maximum area. Now first, what is going to be the height we are going to consider for this area? The height we are going to consider is going to be 3, because this is the height of the smaller edge. The length in this case is going to be 4 minus 2. So length is going to be 2. And the total amount of water we would be able to store is going to be 6 units. So let's just consider, because it's water, we can consider it to be liters. So 6 liters of water we can store in this container. And this is the biggest container or maximum amount of water we can store. So let's try to see that what could be different ways to solve this problem and how we can use 2 pointers to find the optimal solution. And for that, I have actually drawn a much bigger problem, and this is going to help us visualize the problem, and also at the same time we would be able to make some interesting suggestions. So what is going to be the most simple brute force approach? Well, most simple brute force approach is pretty common, that we take, suppose we are making a container using this value, then we see that what are different possibilities of all the containers we can make, and what are going to be the different areas of all of those containers. At the same time, we are going to have a max variable, and that max variable is going to keep track of what is the maximum area we have calculated so far. So first we would take all the containers using this value number 1. Then we would take all the containers using this value number 2. So we would make a container like this, then we would make a container like this, and then we would make another third container like this, and depending on the positioning, we would keep on making the containers. Every single time we would be recording the maximum value. This is guaranteed to give us the correct answer, but again the solution is going to be big O of n square, which is not what we want. We want something smarter, better, faster. So what could be the another solution? Now, unlike the previous explanation, in this case you cannot use binary search, because definitely there is no sorted property or there is nothing to be searching for. Essentially all we need is a way to find maximum amount of water. So let's see how we would be able to use 2 pointers in this scenario. Again, as always, we are going to have our 2 pointers. So first pointer is going to be located at the first position. So this is going to be our starting pointer. This is going to be our ending pointer. Now between the starting and ending pointer, what we are doing is, since they are so far away from each other, they form the maximum length possible. So length portion we are already considering to be the highest length, and since they are going to come towards each other, the length is slowly going to decrease. But what would increase is the height, because there are different height positions or different height combinations, because over here a single height makes no difference. We need to worry about the combination of any two heights, and that is going to give us that how much amount of water we would be able to store. So in this case, height would be the variable factor. Since height is the variable factor, why don't we make our traversal decision based on the height? And how we are going to implement height as our traversal decision is that first of all we are going to check that what is our purpose. Our purpose is to find the maximum area. Maximum area can be maximum only if either the length is maximum or the height is maximum. So the only way we are going to move one step to the left or one step to the right is by keeping the value with higher height constant and the value with lower height to move to the next value. And this is how we would be able to find the maximum container value. Still confused? Let me quickly show it to you through a live demo. So in this case, we are going to have a max variable that is going to keep track of maximum amount of water we have calculated so far. Currently, the difference between these two, the length is going to be 8. If we see height difference, we are going to choose the minimum height amounts to. So this is the minimum height, which is 1. So the area is going to be 8 times 1. So maximum area we have found so far is 8. That is acceptable. Now in this case, is it more beneficial to move the end value towards left or is it more beneficial to move the starting value towards right? Obviously it is more beneficial to move starting value towards right. Why? Because this value is already smaller. So there could be possibility that in future, if we get a greater height and we keep this bar, this edge, then we could have a bigger container. But if we move on the left hand side, again the maximum amount of water we would be able to fill is going to be determined by the smaller height that was initially located. So in this case, since S is located at the smaller position, we are going to update the position of our S. So currently now S is located at value number 8. So this is the height and this height is 7. And again now the length is going to be 7. What is the maximum amount of water we would be able to fill? It is going to be, we would consider this height to be 7. So 7 times 7, it is going to be 49. 49 is greater than maximum. So we would add 49 as the answer. Now again in this case, it makes more sense to move the ending pointer because the height of this one is greater. So now we would move, since we are moving it over here. Now again this value is decreased, and then we are going to consider another water between this portion, and that is going to be 3 multiplied by 6. So that is going to be 18. This is not going to be the maximum. So again we are going to move to the next value, and for the next value again we are going to move it to the value number 7. So this is going to be our end variable, and then the height is currently same, and the distance in this case is 5. So this is going to be 8 times 5. 8 times 5 is going to be 40. 40 is still not greater than whatever the maximum amount we have found so far. So again we are going to keep on repeating the same process, and eventually we would come at the position where starting and ending position are next to each other, and they would be able to cross each other. That moment we would stop our traversing. Whatever the maximum water we have found so far, we would return that as the answer, which in this case is going to be 49. That is superb. That is the most wonderful way to solve this problem. And if you see what we did, we basically used 2 pointers, starting and ending pointer. If we see time complexity, in this case the time complexity is going to be big O of n, because we are simply iterating over the given input array once, nothing more than that. If we see space complexity, even the space complexity is going to be big O of 1, because apart from using like 3 variables, we are not using any additional space or any additional data structure to store the space. So this is a very wonderful way to solve this problem. And that is how we are going to remove duplicates from the sorted array. Now all of the previous 2 questions I mentioned, I have already solved them on my channel, so I didn't show that what companies have asked that problem, but they are really popular problem. For this one, the LeetCode problem number 26, if we see some of the popular companies who have asked this question, there are companies like Apple, Facebook, Amazon, Microsoft, Google, Bloomberg, LinkedIn, and Intel. They have all asked this question. So that is why this is a really important question. And let's just quickly go through that what is the problem statement, and then we would try to make the solution. Now in this case, if you want, you can again read this whole thing. I'm just going to explain it to you quickly. The problem we are given is that we are given a sorted array. That is cool. Always love when the array is sorted, makes things life so much easier. Now in this case, we are told that it could be possible that sorted array can have duplicated entries. So the moment we identify duplicated entries, we don't care about all the duplicated entries, but the thing we care about is that in the initial portion of the array, all the distinct values has to be present. All the other values, we can mark them as anything like X or underscore or hash or whatever you want. We don't care about those values. So in this case, we are given an input array with 7 characters. But if we see the number of distinct characters we have, we only have 0 as a distinct character. Then we have 1, 2, and 3. So 0, 1, 2, and 3. These are the only distinct characters we have. Now for these 3 characters, we don't care anything. So we are not going to mark them. Basically, they were duplicate entries and we are not concerned. But in this case, we are concerned with the distinct characters. And the moment we find the distinct characters, we need to put them at the beginning and then return whatever the solution we have been able to find. So what is the brute force way to do this problem? Again, brute force way is pretty simple. We just take one value and we will try to see that, okay, how many duplicates there is one, and then we add that, then keep on repeating the same process. And then if this is a duplicated entry, again, we move on to the next value. So this approach is guaranteed to give you the answer in big O of n square solution. So brute force is always not a good way to go. The next way to go is that we can actually try to do something smarter here. And what we are going to do is, obviously, you know, this is a 2-pointer solution, so of course we are going to use 2 pointers. But since we are using here 2 pointers, we are also going to find a way to store the index value. So we are going to have an index value and we are going to initialize it with starting position 1. Now this first value is guaranteed to be a distinct value, because we are told that there is at least one value in the array, and that value has to be part of the original distinct value. So we are going to directly put it over here, and that is why we put the index pointer at value number 1. Now index pointer is just a way for us to iterate over. And also these 2 pointers, what we are going to do is, initially they are both going to be located at the same place, but the end pointer is going to move few steps ahead till it finds a new distinct value. That is what it is going to do. So in this case, currently starting and ending pointer, so this value is same as this one, so we need to skip this part. So we are not going to care about this value, we are going to move to the next value. Now our starting and ending values both are located at this position. This is a distinct value. The moment we find a distinct value, since we find the first distinct value for this index position number 1, we are going to add it over here. So we add value over here. The moment we add the value to our array and we find like a new distinct value, we are going to do index plus plus. So now our index value is going to be 2, and the next distinct character we find, we are going to add it to position number 2, which we find immediately we find it, because this is a new one, because the end pointer went there and it didn't find any duplicate values. So again 2 comes over here and our index value gets updated to value number 3. Now we currently the scenario is that our starting and ending values both are at the same position. So currently the starting pointer is located over here, ending pointer is located over here. Now this ending pointer is going to go one step further. So currently ending pointer is at value number 2. Again, this value number 2 is the same as the previous value. Since it is the same value, starting pointer is going to remain here. Ending pointer was here, it didn't find anything, so now ending pointer will go to the next value. Next value is a distinct value. Again, distinct value, starting and ending pointer becomes at the same position. Index value becomes 4, and the value we added to our input. So we added value number 3 to our answer. Now again at position number 3, ending pointer go to the next. This is already 3. Now ending pointer tries to go to the next, array ended, so we can't do anything about it, and this we can return it as the answer. We don't care about these values because that is none of our concern. But you see, even in this case, rather than coming on one side, starting and ending pointers were working in tandem to go from one step to the other step to find the answer. This was an easy problem, and in this case I intentionally chose this problem because we are at the same, apart from using 2-pointer solution, at the same time we are also using sliding window technique, because we are creating a window between starting and ending pointer, and the moment we find some solution, reasonable solution, we shift our window depending on the conditions. And this is a beautiful way to solve this problem, and that is why I decided to keep this solution at the last. So I hope this explanation makes sense to you. I know that explanation is the one part, but you have to practice on your own in order to master all of these techniques. So please go ahead, practice as much as you can, and let's hope you find this useful in your day-to-day life or your coding interviews. Thank you. Hello friends, so today we are going to study about the intervals coding pattern. This coding pattern has been asked in probably thousands of interviews, because intervals coding problem is actually a real life scenario that we use daily in lot of applications. Typically, first let me explain what intervals coding pattern is and where you can identify it. Typically, this coding pattern is associated between these data structures. So data structures, fixed data structures like array, linked list, string, and also heap, that uses typically interval type of problems. How do you identify an interval problem is that in most of the cases you are given some time sequence, and in that time sequence you are being asked specific different intervals that are separate from each other, or somehow they overlap between each other, and you might be given task to find like a common window or a common space between any two set of variables where you can find some value that is empty in between, and you want to schedule a meeting. So in this example, suppose these are the two different calendars for two different people in working in any company, and you want to find like empty spaces to book a meeting. Then you can find these slots that are available on both the cases where you can book the meeting. This is a very good internal type of interval type of question. Second problem we can find is that suppose rather than this, you are given only just like a single time sequence, and you are given some scenario where you are given some different intervals, and you are told that this is a new interval that you want to merge over here in such a way that there is no overlap between any existing intervals. So these are just like few of the problems. If we see some practical applications for the interval type of problems, there are practical use cases, as I mentioned, such as like calendar management, or sometimes if you want to do like project management where everything needs to be done in a sequential manner and where there is a dependency between one item after the other. So one has to be done in order to complete the second one. So even in project management or calendar management, or like to find a room or find a meeting slot, something like that, these kind of questions typically use intervals, and today we are going to go through every single one of them. So first let's see that what are the typical possibilities we have in any given interval kind of a problem. In this example, I'm using this blue one as interval A and this B or the yellow one as interval B. And we are going to see that based on this pink time sequence, what are different possibilities between A interval and B interval, and how can we handle them. So first possibility is pretty simple, that A interval and B interval are located at different time spaces. So there is no correlation between them and they do not overlap between each other. So that is perfectly fine. Second possibility is that before A interval ends, B interval begins, which means we can find that there is an overlap between this portion. So we might be asked to do something over here. We could have been asked some question that if we see any overlap, we need to get rid of the overlap, or we need to like merge these two. So suppose if we are being asked that we need to merge any overlaps, in this case, we would create an entirely new interval that looks like this, where we are going to take the starting point of this A value, and we are going to use the ending point of this B value in this time sequence, and then both of these times or both of these intervals would be merged into a single interval. So this is a very good type of interval problem. If we take a look at this example, in this case, interval A completely overshadows interval B. So basically we can say that B is completely in between the bounds of value A. So even there will be scenarios where you will have to deal with situations like this. Now this one is the reversal of this situation, where we are starting with B and ending with A for this entire merge interval. Same way, this is the reversal of this previous example, where now B is completely overshadowing the value A. So in this case, if we have to merge these intervals, there will be a single interval like this. And in this case, since B and A are located at different places, there is no overlap between them. So we don't need to basically do anything. And if we are being asked to find like an empty spot, we can easily find an empty spot between these two portions for these two intervals. So these are just like few of the possibilities that you will have to deal with. And when I say few, I mean all the possibilities that you will have to deal with, because there are only 6 things you can do with any two intervals. In order to better understand the interval problems, let's see some examples. In this case, I'm going to show you 3 different examples. First example is really popular. Second example is like moderately popular and also covers very important key topic. And the third example is actually a LeetCode premium problem. So no, I know not many people have access to LeetCode premium. So that is why I decided to show these 3 examples. So let's just start with example number 1. Now this first example is the merge interval example. This is LeetCode question number 56. And in my opinion, this has to be one of the most popular LeetCode problems, because even right now, if you see that not many companies are hiring and there are hiring freezes going on all over the world, still this question has been asked by staggering number of companies multiple times. There are companies like Bloomberg, Amazon, Uber, Facebook, Google, Microsoft, Apple, Nvidia, Morgan Stanley, ByteDance, Snapchat, Twitter, Goldman Sachs, and Tesla, to name a few, who have already asked this question recently. So that is why you can imagine that how popular this problem is. So let's take a look at this problem. This one is the LeetCode medium problem, and as mentioned, this is like one of the most liked problems on LeetCode, and the problem statement is really simple. Basically, we are given an integer array of intervals where we are given the values in the form of tuples. So we are given different tuples of interval array, and we are given in a sequence such that every single tuple represents an interval that has a starting value and an ending value. Now we need to merge all the overlapping intervals, nothing more than that. Pretty simple. And when we are done with our merging all the intervals, basically we need to return an array that does not contain any overlapping situation, or all the non-overlapping intervals are present. Let's try to understand this with a couple of examples. If we take a look at this first example, so now I have plotted all of these 4 intervals in a time sequence, and our aim is to find all the overlapping intervals and merge them. So clearly we can see that there is an overlap between these 2 intervals. Question is, how do we identify that there was an overlap between these 2 intervals? Well, the answer is quite simple. Before this first interval ends, the second interval begins. Let me repeat. Before we find the ending value of the first interval, if we find an interval that has a starting value before the ending value of the previous interval, which means we can define that there has to exist an overlap between these 2. So this is the most basic definition to identify an interval. In this case, we identify that there exists an interval over here. So we will have to do a merge operation. In order to do a merge operation, the answer is quite simple. We are going to take the least amount between the starting values, which is in this case the value number 1. And we are going to take the maximum amount between the ending values. And in this case, the answer is 6. So we are going to create a new sequence that is going to look like this. And in the answer, we are going to create a merge interval between these 2 intervals. And these 2 are not already non-overlapping intervals, so we are not going to touch them. And this is the answer we need to return. Now let's take a look at the second example. In the second example, we are simply given a smaller 1 to 4 and then 4 to 5. So in this case, we are given a line like this. First interval is 1 to 4 and second interval is 4 to 5. Now even in this case, 4 is the middle point for both of them. So the answer is going to be that we are simply going to create an interval that is starting value from 1 and ending value is at 5. And we are going to return that as the answer, which we can see mentioned over here. For this problem, also one more thing that I'm going to explain that is not shown in this problem, and that interviewer is going to focus on, is that currently in both the examples, all the values we are given, they are sorted based on the starting value. So the smallest starting value is located at the first in terms of the intervals, and all the other they are in like ascending order. So that is why we can clearly see in this case that okay, this is the overlap and we can resolve it quickly. But in the actual scenario, that is not a requirement. So it could be possible that the given inputs are not in sorted manner, and we will have to find some trick to solve this one. There is also one more thing with this problem, and that is that to find the optimal solution for this problem is easier than finding a non-optimal solution, and that is tricky. So in the end, I'm just going to show you like a very small non-optimal solution, but that you can use sometime in the future, or if you just mention it in your interview, it is going to amaze your interviewer. So first, let's see a quick example with the optimal solution. Okay, suppose this is the input we are given, and now we need to find all the merge intervals. Now, if you see this input, it becomes really difficult to find like what are the intervals that are doing or that are overlapping with each other. So now what would happen is that for say for example, we are this interval 1 to 9. If we want to identify that does there exist any other interval that overlaps with this interval, then we will have to go through every single value inside the given input and then make some changes. Same way for 2 to 5, again we will have to repeat the same process. So basically if we keep on doing this, this is going to lead us to solve this problem in big O of n square time, which is not what we want. We want a better solution, and the better solution can be achieved if we simply sort this given input. And how we are going to sort this given input? We are going to sort this based on the starting values. So the smaller starting value is going to be located at the first positions, and the larger starting values are going to be located at the last positions. And after sorting, things will become much more easy for us. So let me just quickly draw the sorted solution, and then we will see that what would be the trick to solve this problem. Okay, now we have our sorted input ready. Now things are going to be much more easier for us. Basically, what we are going to do is we are going to create a new merge interval array, or inside the new merge interval array, first of all, we are going to check that, okay, this is the first position that we will have to add. Okay, so let's just add this first position, 0, 3, we already added. Okay, now for the second position, there are two possibilities. First possibility is that either these two, they do overlap or they don't. Now, in this case, how do we check that whether they overlap or not? We check it based on the starting and ending values of this existing variable or this existing interval, which is 0 and 3 in this case, and we check it with the starting value of this new interval. So because starting value of this new interval falls between the ending and starting values of this previous interval, we can define that there exists an overlap. Now, if there exists an overlap, then there are two possibilities. We basically need to find the starting and ending values for each one of them. Starting value is going to be the lower value between both of the intervals. Ending value is going to be the higher value, and that is simple. That is all we need to do. And if we keep on repeating the same process with all the elements that are next to each other, eventually when we reach to the end, we would have find a new set of array that does not contain any overlapping intervals, because we would have merged every single one of them. And let me quickly show you how we are going to do it. So first we find, okay, 0, 3 and 0, 1, there is an overlap. Now, because there is an overlap, we will have to choose what we need to add. We are going to pick the lower value between 0 and 0, lower value is 0. Higher value between 3 and 1, higher value is 3. So 0, 3 is going to be the overlap. Now we are going to get rid of this first element, and now we are only going to focus on the second with the next element. So currently this value is 0, 1, this value is 0, 2. Again, 0 falls between the values 0 and 1, so there is an overlap. We are going to see, okay, what is the smaller value? 0. 0 is already present over here. What is the greater value? 1, 2. But we do not care about 1, 2. We will have to compare the greater value with this one, because this is the entry we already added. So now we are going to compare this 3 with this 0. In this case, because 3 is greater, again we are going to get rid of this one. We can also get rid of this one, and now we are at this position. Again we are comparing it with this one. So now, okay, 0 and 3 and value is 1. 1 is between 0 and 3, which means there is an overlap, and we are going to create a 0 to 9 over here. Now again we are going to get rid of this one. Now we are going to compare it with 2 to 5. Again 2 and 0 to 9, so 2 falls between, so there is an overlap. Definitely between 2 and 0, 0 is smaller, so we are going to keep 0 as it is. For this 5 and 9, 9 is greater, so we are going to keep 9 as it is, and we are going to get rid of this one. Now we are at this position. For this next position, the starting value is 10. 10 is greater than the ending value of this previous interval, which means there is no overlap. Because there is no overlap, we would be able to add this 10 and 11 as it is. Now after adding 10 and 11, now we are no longer going to compare with this 0 and 9, because we already found that 0 and 9 are located at the correct position due to the sorting property of original input that we have modified. So in this case, since this is 10 and 11, now we are going to compare 10 and 11 with 12 and 20. So again, 12 is greater than 11, so which means there is no overlap between these two, so we can add 12 and 20 over here. Awesome. Now after adding 12 and 20 over here, we see, okay, this value is 19. So 19 is less than this value 20, which means that there exists an overlap between these two values. Because there is an overlap, we will again have to repeat the same procedure. So the procedure we are going to repeat is between 12 and 19, we are going to pick the smaller value, which is 12. Awesome. Between 20 and 20, we are going to pick the greater value, which is 20. Awesome. So in the answer, we are simply going to have these three values that we are going to return. First interval is 0 to 9, where we merged bunch of different small intervals. Second one is 10, 11, because it was not overlapping with anyone else. And the third one is 12, 20, because there was an overlap between these two intervals. And this is the full solution of this problem. Now, if we see the time complexity for this one, the time complexity is actually going to be big O of n log n, because n log n is needed to do this or to generate this sorted result. And then we can solve this problem in big O of n times. So it's going to be big O of n log n plus big O of n, but in general we can write it as big O of n log n. If we see space complexity, now this is debatable. You can argue with your interviewer that because we are creating a new array, we can consider space complexity to be big O of n, or if the answer by itself needs us to create a new array, then we can consider the space complexity to be big of 1. So this is debatable. You can discuss with your interviewer what you want to do to solve this problem. Now let's just go. Now I have shown you the optimal solution. Now let me go back and show you the non-optimal suboptimal solution where we can solve this problem. Suppose we are given a set of interval that looks like this. Okay, so suppose this is the input we are given. Now I'm showing you suboptimal solution for your knowledge only. So what we can do is we can create a graph solution and we can find all the connected components, and then we would be able to solve this problem quite easily. What we are going to do is we are going to treat every single value as the node in a graph. And remember, graph is made out of two things, node and edges. So as a node, we already identified that these are all the tuples that are considered as node. What we are going to treat as the edge is the fact that if there exists a value, so say for example, this 1 to 5 is a node. Okay, so let me create a node over here. Now, if there exists a value where the starting value is between 1 to 5, then we would extend an edge from this node to that next node, which in this case, this value is 4 to 7. So 4 to 7, the starting value is 4. And because starting value is 4, we can actually create an edge between these two, stating that these two are connected. And what we mean by connected is that there exists an overlap between these two values and we will have to resolve them. So this is first way. Second thing, again, we are going to repeat the same thing. Okay, so let me just take down this value 6 to 10. Again, we are going to create a node 6 to 10. And then we will try to find, okay, does there exist any value that starts between 6 to 10? Yes. The starting value of this value number 6 is actually between these values 4 to 7. So we will extend an edge between these two values as well. Now notice in this case, there is no edge between this value 1 to 5 because this one is only limited to 1 to 5 values and the starting value of this one is 6. So hence there is no edge between these two. Again, if we take the next example, 15 to 17, okay, 15 to 17 is the new node. And if we see 16 to 20, so the starting point of 16 is actually between 15 to 17. So again, we can extend an edge over here. And for this new tuple, we are also going to have a new connected component. And again, there is no correlation between these two. Now, all we need to do is that all the values that are connected with each other, we will have to resolve them and put them in one single merged block. So in this case, what will happen between these two values is that from 1 to 5 and 4 to 7, we can clearly make a new node that is 1 to 7 because we are taking the smaller value of the starting point and the greater value of the ending points. Again, between this 1 to 7 and 6 to 10, what we can do is we again take the smaller and larger value. So the answer is going to be 1 to 10. So from these three connected components, we can actually make a merged node that is 1 to 10. And from these two connected components, we can make another merge node that is 15 to 20. And these two are what we need to return as the non-overlapping conditions. This is just for an example purposes. This is a suboptimal solution. Why this is a suboptimal solution? Because in order to generate this graph, it is going to take us big O of n square time. And that is why the time complexity is actually suboptimal compared to our optimal solution. Now let's move on towards the second example. In the second example, we are actually going to learn about that how can we insert an interval in any between any two intervals, and where we are going to do the reverse of what we already did. If we see some of the popular companies who have asked this question, there are companies like Google, Amazon, Facebook, Microsoft, LinkedIn, Apple, Bloomberg, ByteDance. So they have all asked this question, which means this is a popular question. And if we take a look at the problem statement, it states that basically we are given an array of non-overlapping intervals where we are given the definition that any single tuple inside the array defines the starting and ending point of the interval. We are also given a new interval and we are also given the starting and ending point of this new interval. And we simply need to insert this new interval in our existing set of intervals. We are also told that we need to make sure that there does not exist any overlapping intervals after we add this new interval. So if there is an overlap, we will have to simply resolve that. In this case, a good thing we are told is that all the original input intervals, they are already sorted in the ascending order based on their starting values. So this is a huge benefit for us. So first, let's try to understand this with an example. In this case, we are given two intervals already. So first one, the value is 1 to 3. So let me, okay, 1 to 3, and second one is 6 to 9. So that is 6 to 9. If we see the new interval we are trying to add, that is 2 to 5. Okay, so 2 to 5, 2 will fall someplace over here and 5 will fall someplace over here. So 2 to 5 is the new interval we try to add. If we add this new interval, what is the answer is going to look like? Again, it's pretty simple. 1 to 5, this is going to be the first interval after we merge these two, and then 6 to 9, since we are not doing anything, we can simply keep it as it is. Solving this problem is actually quite simple. How we are going to do it is that if we simply just go iteratively, so say for an example, we are given an input that looks like this, where we are given, okay, this is the first interval, this is the second interval, and this is the third interval that we are given as the input. We can put any arbitrary values. Okay, it's 1 to 3, then 5 to 7, and then 9 to 11. This is okay so far. We are given a new interval, new block that we are trying to add. This new block is spanning between the values, let's say these values. So the value is 2 to 6. This is the new block we are trying to add. What we can do is, first we will see for the first block, we will see that whether this first interval starting and ending value, does they merge with, or does it overlap between the new interval we are trying to add. Since the starting value of this new interval falls between these two intervals, which means immediately we will have to run the overlap function. So if we run the overlap function over here, the answer we are going to get is, we will start, okay, so this is going to be the value number 1, and this is going to end at value number 6. And currently I'm just merging these two intervals, nothing more than that. So this is the first, after first iteration, and meanwhile we already have our existing values. So 5 to 7 is still present, so we will have 5 to 7, and also 9 to 11 is still present, so 9 11 is also present. Again, if we do repeat the same process, so between this interval, again we will do the overlap. After doing the overlap, basically we would end up with a new interval that looks like 1 to 7, and we can get rid of all the previous one, and this one is already 9 to 11, and since there are no overlap right now, we can return this as the answer after inserting the new interval that does not break any, or that does not create any overlap. But what would be the most optimal solution? Well, this solution works perfectly fine. If we see time complexity is actually going to be big O of n, which is pretty good. But the thing is, whenever, this is a golden rule I'm talking about, whenever you see any input where the given input array is actually sorted, if that is the case, if the given input array is sorted and you are able to solve this problem using big O of n time, then if you use the sorting property and if you use binary search, you would be able to solve this problem in big O of log n time. This is a great tool to remember because you are going to use it a lot of times in many different problems. So again, if we are going to use binary search in this problem to solve this problem in big O of log n time. Now in this case, because I'm using binary search, I'm not going to show you this small example because it has very limited test cases. Let me just draw a bigger case, and then we will try to see that how to best use the binary search in any given situation. So suppose this is the input we are given. Let me just mark some arbitrary values. Now the new block we are trying to add is that it is, say for an example, it is between these two values. So value is let's say 6 and 10. This is the new block we are trying to add. Now, since I already know that the starting value of this new block is already 6, do I need to go through every single one of the intervals to see where there could be a potential overlap? No. What I can do is, since I already know that all of these values are sorted and there is no overlap between any of the existing input results, simply using these values, I can try to find that, okay, what is the interval where there could be a potential conflict, and that I can pretty easily find over here. So simply I can see that where does 6 fit between all of these starting values, and immediately the answer is that 6 between the values 5 and 9. And now all I need to do is that for this interval 5 to 7, does 6 fit between them? So yeah, 6 fits rightly over here. So I can definitely know that I will have to do a merge operation over here. I know how to do the merge operation, picking the smaller values between these two and picking the greater values between these two. After picking the smaller and greater values, we have already eliminated the starting position of this one. So we already took care of this part. But now we will have to take care of the ending part as well. Now for the ending part, again what we need to do is, we already know that all the values are stored in the ascending orders, which means we can say that which is the block after which definitely there cannot be any kind of overlaps. So we find that the first value that is greater than 10, and that is the start of an interval, that is 13. So we can clearly see that all of these values, they are never going to be a part of any overlap that would be caused by this interval, because the ending value is 10. So we will check one previous value. The previous value is currently 9 to 11. 10 falls right between them. Because 10 falls right between them, we are going to do a merge operation, and eventually we would create a new value that is between 5 to 11, and all of these values, so 1 2 3 and then all of these 13 to 15 and so on and so forth, they are all going to be as it is. Now notice that even though we had like 5 different intervals in the input, we only did 2 calculations because we used the binary search property of this original given input sorted array. And that is why things became much more easier for us. If we see time complexity now, the time complexity is actually going to be big O of log n, because this makes life much more easier to do the search operation. Okay, now let's just quickly go through this remove interval problem. This is a LeetCode 1272 number problem, and this is actually a LeetCode premium problem. So that is why I decided to solve this problem, because I know not many people can afford the LeetCode premium subscription, and since I already have it, I want to make the most use out of it. This is a LeetCode medium problem, and in this problem, basically if you want, you can read this whole statement, but I'm just going to explain you that what it is asking us to solve. We are simply given an array of intervals that defines some intervals that we are already given, and these are already non-overlapping intervals. That is good in our favor. We are also given a new interval that we need to remove, which means if we remove this new interval, all the intervals that it overlaps, they needs to be removed from this original input list, and then we only need to return a new list of arrays or new array list that contains all the intervals that are not part of this to be removed part, and that is the answer we need to return. So let's just try to understand this with an example. Suppose again, just like this, we are given an interval that looks like this, and let's just give values 1 3 and then 5 7 and then 9 11. Okay, and then we are being asked to remove an interval that looks like this one. The value is 2 2, let's just say 6. Okay, this is what we need to remove, which means we can still keep this portion, but we cannot keep this portion. This we will have to get rid of, and even until this portion, everything needs to be getting rid of, but this portion we can still keep. So the answer in this case is going to be that first we will have an interval bit that is 1 to 2, then we won't have any interval until the value 6, but after the value 6 there exists an interval between values 6 and 7. So again, between 6 to 7 there is going to be a new interval, and then this 9 to 11 is going to left untouched because it was not part of this 6 to 11. So what the simplest solution we can do is, and in my opinion this should have been a LeetCode easy problem, not medium problem, but anyways, LeetCode has their own ways to decide. What we can simply do is, whenever we are given an input and we are also given the interval we are trying to remove, so if we just take a look at the same example again, basically what we can do is that simply we can check for every single interval that we iterate over to see whether it conflicts with this new interval that we are trying to get rid of. So in the first place we check, okay, this value is 1 2 3, and the value that we are trying to get rid of starts at value number 3, which means that there exists an overlap between these two intervals. So because there exists an overlap, we will have to do something, and what we are going to do is we are only going to pick the values between this 1 and 2. So between these two starting values, we are going to create a new interval and store it in our answer. So 1 to 2 is going to be the new interval. Then this part we don't care. Okay, now we are on the next interval. Again, for the next interval, we are going to check that does its ending value is greater than the ending value of the part we are trying to remove. If that is the case, which means there is a possibility that this interval will have some value that we can add in the answer. Suppose over here, if we had one more interval that looks like this, okay, I'm just giving you an example, then this interval has to be removed completely because both of their starting and ending value falls between these two portions. So then we can't do anything in this case, which means that this interval is no use for us, so we will simply skip to the next one. But in this case, since this interval already has a value that is greater than the ending value of the part we are trying to get rid of, so then the value difference between the part we are trying to get rid of and the ending of this current variable, so that is 6 to 7, that would be stored in our answer. So 6 and 7 would be stored, and then all the other values, so in this case 9 and 11, will be left untouched, and we can add it to the answer. And this is the whole solution. Now if we see time complexity, in this case the time complexity is simply going to be big O of n, because we might have to iterate over every single value inside the given input. And in terms of space complexity, well, this is debatable. You can argue with your interviewer, since in this case we are explicitly told to create a new list and return that. We are just simply creating a new array list, and then we are adding all the solutions to that. So in this case we can mark the space complexity as constant. But if we are not being asked and still you are using a new array list, then it could be considered as big O of n. So you can discuss with your interviewer on how you want to treat the space complexity as. Hello friends, so in this video we are going to learn about fast and slow pointers. This is a really popular coding pattern technique that is used in a specific type of problem. This is also known as a rabbit and a tortoise problem, or hare and a tortoise problem. In this method, basically we use a fast and slow pointers to move across any array or any linked list. So in this video, I'm going to explain you three things. First, I'm going to explain you that what this fast and slow pointer technique is. Then I'm going to explain that where it is applicable and what type of problems it can solve. And then I'm going to show you three different real life lead code examples that are being asked in bunch of different companies multiple times. So first, let's understand what does a fast and slow pointer approach means. As the name suggests, we are going to use two different pointers. First one is going to be a fast pointer and second one is going to be the slow pointer. They both are going to start at the same time, but there is one key difference, and the key difference is that fast pointer is going to take multiple jumps. So it can be like 2 jumps, 3 jumps, 4 jumps, something like that. In meanwhile, it is going to take multiple jumps faster compared to the slower pointer, which is only going to take one jump every single iteration. So slower pointer is going to move in the conventional manner of the way we move pointers. But fast pointer, let's say for this example and most of the example, you are going to consider it as taking 2 jumps at a time. So moving twice faster than the slower pointer. So in the first iteration, slow pointer is going to come over here. Meanwhile, fast pointer is going to come over here. During the next iteration, again, slow pointer is going to end up over here because it will take one more jump, but fast pointer will end up over here. Same way, if we do one more iteration, basically slow pointer is going to end up over here. Meanwhile, fast pointer is going to end up over here. So with every single iteration, we would be able to see that the difference between the slow and fast pointer keeps on increasing, and eventually what would happen is that fast pointer would keep on jumping 2 steps at a time and it would reach to the end of our given input. So in this case, we are running it over array, and meanwhile slow pointer would be somewhere in the middle, and that would be able to give us some important information. Same thing can be applied for the fast and slow pointer in the linked list as well, where even for the linked list we will have both fast and slow pointer starting at the same position, but fast pointer is going to take 2 jumps at a time and it would reach to the end much quicker in 3 iterations only. Meanwhile, for slow pointer, in this case, after 3 iterations it is going to stay somewhere over here, so somewhere in the middle. And that brings us to the next point, that where do we actually use fast and slow pointer. And I mentioned that when the fast pointer reaches to the end, slow pointer is somewhere in the middle, and that is exactly one of the most popular use cases of a fast and slow pointer technique, where if you are given any single array or any single linked list and you want to find the middle point of that value, then if you use fast and slow pointer technique, you would be able to find the middle pointer quite easily without using any extra additional space, because the fast pointer would reach to the end and during the same amount of iterations the starting pointer would have reached to the mid pointer, and that way we can return the middle of the array or linked list quite easily. So this is one of the very popular use case. But the second popular use case that is even better than this one is to detect cycles. And you would be asking that how can we detect cycles using fast and slow pointers. So this I'm going to show you next during one of the examples. But remember, these two are very important use cases that we typically use for a fast and slow pointer technique or a hare and tortoise kind of a problem. So now let's jump on to the examples. And if we see, the first example I'm going to show you is to find the middle of a singly linked list. As I mentioned that we can use fast and slow pointer technique to find the middle of any linked list or array. And this has been an important problem and asked in some of the most popular companies like Adobe, Amazon, Apple, Facebook, Google, Uber, Microsoft. So you can imagine that all of the top companies like asking these kind of problems. So let's just go to the problem statement. And basically the problem statement is quite simple, that we are given the head of a singly linked list. Now, if you know anything about singly linked list, in the singly linked list, we only know that what is the next pointer value from the current node, nothing more than that. We don't know how many total number of nodes are present. We also don't even have the ability to go back to the previous node. So in this case, finding the middle pointer could become a little bit tricky. But the trick, you already know what we are going to use is that suppose we are given any single linked list. Basically we are going to use two pointers, and one is going to be the fast pointer and second one is going to be the slow pointer. So in this case, I'm taking five element linked list, and let me just mark it as 1 2 3 4 5. So if we use fast and slow pointer, this is going to be the fast pointer, this is going to be the slow pointer. Fast pointer is going to make 2 jumps at a time, so fast pointer is going to end up over here after the first iteration, meanwhile slow pointer is going to end up over here after the first iteration. Now every single time we will check that whether the fast pointer is located at the end of the linked list or not. How can we determine? We can determine by checking that if the fast pointer value, if that is equal to null, then we know that we have reached to the end of the loop, because it could be possible that say for example, for some reason fast pointer is at here, and if it tries to take 2 jumps, it would not be able to do it because it will reach to the value that is null. So that way we can determine that fast pointer has reached to the end of the loop. The second possibility is that the fast dot next is equal to null. That is also means that now currently fast pointer is located over here, and the next value from this one is a null value. So if we take a look at these two conditions, we would be able to determine that whether fast pointer is at the end of the loop or not. Now in this case, during the second iteration, fast pointer is going to end up over here, and during the second iteration again slow pointer is going to end up over here. Now if we do fast dot next, then we would be able to find a null value, which means this is the end of the linked list. The moment we identify that the fast pointer is at the end of the linked list, which means whatever the position of the slow pointer is, this is going to be the middle pointer of our linked list, and this is the whole solution. And you see how efficiently and how beautifully we were able to come up with the solution because we use fast and slow pointer. Try to imagine if you want to solve it other way, like the conventional way. What would be the approach you would take? You would have a counter called n, where you are going to mark that what are the number of nodes this currently linked list have. Then you are going to have a pointer, and then you are going to move that pointer all the way towards the end. The moment you reach to the end, you would have your value n that says that there are 5 elements in the linked list. Then again you will start from the beginning, and then again you would reach to the element number 3, and then you would return that this 3 is going to be the middle of the linked list. So this is going to be the conventional solution. But because we use fast and slow pointer, we were able to complete this whole solution pretty quickly in a single iteration, only with 3 different type of iterations inside the linked list. So if we see time complexity in this case using the fast and slow pointer, the time complexity would typically be big of n divided by 2, because remember, this fast pointer doesn't have to jump through every single value. It takes 2 jumps at a time, which means we are already saving some iterations in our algorithm. But in general, if you would have to write it, you can write it as big of n. And you know, the another beautiful part of this one is that the space complexity for this approach is actually big of 1, because we don't need any other data structure where we need to store some value. So this is the time and space complexity, and this is a beautiful approach that you are able to solve using the fast and slow pointer. Okay, so let's see the coding solution for the middle of the linked list problem. Basically, first of all, we are going to initialize 2 pointers, fast and slow pointer, and we are going to position both to the head of our given list node. Now we are simply going to run a while loop that while fast is not equal to null and fast dot not next is not equal to null, we are simply going to keep on incrementing the values of slow pointer and the fast pointer, where slow pointer is going to move conventionally to the next element. Meanwhile, fast pointer is going to move 2 steps forward and is going to run twice the speed of the slow pointer. The moment this while loop ends, the position of the slow pointer is going to be the position of the middle node, and we are going to return that. Let's try to run this code. Seems like our solution is working as expected. Let's submit this code, and our code runs 100% faster than all the other solution, and that is because the runtime is 0 milliseconds, and this is a very simple problem to solve. Let's try to find another example, and that is linked list cycle. Now this is also a really popular problem, and if we see some companies like Amazon, Apple, Bloomberg, Google, Goldman Sachs, Microsoft, Nvidia, Facebook, so they have all asked this problem, which means that this is an important problem. You can at least understand that. Now I already explained you before that how you were able to find the middle pointer, but I haven't shown you that how you can detect a cycle inside the linked list. And if you see, this is greatly like problem on linked list, so which is on LeetCode, so which is pretty awesome. We should always try to aim for more like problems, because they have been widely accepted by communities and the interviewing community as well. So in this example, basically we are given the head of a linked list, and we need to determine that whether the linked list has a cycle inside it or not. So what are some of the examples that we can come up with? So we can have a linked list that looks like this. Okay, let me just quickly draw it. So this is one of the linked list where we can see that there are no cycles. We are just going simply straight forward, and eventually the last node calls the next node as null, which means we can define that this is a legitimate scenario. There is no cycle in this linked list. So if say for example, if we are given an example like this, what would be the best approach to see that whether this linked list contains a cycle or not? We can have a pointer, let's just name it as p, and we are going to move to the next element every single time, and then we would try to see that whether this p is able to reach to the end node that is equal to null or not. If it reaches to the end node that is equal to null, which means that we can for sure say that there are no cycles in this problem. Okay, but this approach is very limited, and it will only work for the cases where there are actually no cycles. What would happen in a case where, say for an example, rather than the 6 pointing towards the next node that is null, this 6 points to the next node that is 3. And now what would happen is that our counter p is going to keep on moving to the next element again and again and again. Eventually what would happen is that p is going to end up over here. Then p would again come back to this 3, and then again p would keep on doing the same thing again and again and again, because remember, this is a linked list, and say this is a single linked list, so we can't even go back, so we don't know. So now what would you do in this problem to solve this one? Well, one approach comes to our mind is that again we are going to use the same single pointer approach with the p, and at the same time we are going to have a hash set. Now what this hash set is going to do is that, say for an example, if we have visited some node already before and that same node appears again, which means we would be able to determine that there is a cycle inside the linked list, and this approach would be able to work as expected, because during the first iteration of this p, for all the elements, these are unique elements, they are not being repeated. So the hash set, we would add all the entries 1 2 3 4 5 6, and then the moment from this 6 we would try to come back to this position, and this node number 3, we notice that this has already been visited. In that case we can determine that because this 3 has already been visited and we are revisiting the same topic again, then immediately we can terminate this and say that there has been a cycle detected, and we would be able to solve this problem. The moment you would give this solution in your interview, your interviewer is going to ask you a very simple problem, and the problem is that what would be the time and space complexity for this approach. The time complexity in this case is going to be big O of n, because we are doing single pointer iteration in like single time. But for the space complexity is also going to be big O of n, because we were using an additional hash set. And your interviewer is going to ask you a very simple thing, that I do not want the space complexity to be big O of n. And now you are stuck, because you were thinking in just one dimension and you were pretty happy that, hey, I found the solution and I'm just ruling this interview and I'm going to get job and whatnot. But that would be a small thing in your thinking. You will have to broaden your horizon and try to think about other approaches, because now you have, your interviewer just told you that, hey, you want to solve this problem in big O of 1 space complexity. Lucky for you, because I'm explaining this fast and slow pointer technique, you already know that what is going to be the solution. The solution is going to be a fast and slow pointer technique for this one as well. And how we are going to use it? Same way we are using all the fast and slow pointer techniques, that we are going to have a fast pointer over here, we are going to have a slow pointer over here. What we will do in this case is that fast and slow pointer are going to move in their own directions if, say for an example, there does not exist any single cycle in this case, and the next point it is pointing to is null. What would happen? Fast pointer would come over here, okay, meanwhile slow pointer would come over here. Again fast pointer would come over here, meanwhile slow pointer would come over here. Now from this position, if fast pointer moves to the next element, it would encounter a value that is null. The moment fast pointer encounters a value that is null, we can immediately say that there are no cycles. So okay, that took care of the scenario where there are no cycles. We can already solve this one. Now what would be the next approach? The next approach is quite simple. Now we need to see that what would happen in the scenario where there exists a cycle. So again, let's just create a cycle in this case, and now let's see that what would happen. Okay, now same way, fast pointer is going to make 2 iterations. So fast pointer is going to end up over here. The slow pointer is going to make 1 iteration. So the slow pointer is going to end up over here. Okay, let me get rid of these two. Again, if we repeat the same process, so now fast pointer makes 2 iterations. So fast pointer is going to end up over here. Slow pointer is going to make 1 iteration. So slow pointer is going to end up over here. Again, let me get rid of the old entries. Same way, fast pointer now again takes 2 iterations. What would happen is that fast pointer would end up over here where slow pointer is already. The moment we identify that the fast and slow pointer are located at the same position, and during the traversal fast pointer came up to the same place where slow pointer was, or slow pointer came up to the same place where fast pointer was, in either case we can determine that we found a cycle. Okay, now in this case fast pointer came up at a place where slow pointer was already at. Let's see what would happen if we had cycle that is located from the 6 to 2. What would happen in this case? Okay, again fast pointer, fast pointer, fast pointer, and for 3 iterations there is going to be slow pointer, and slow pointer. This is the current scenario. So now let's just get the latest values. So these are the fast and slow pointer entries. Now if the fast pointer takes 2 jumps, the fast pointer is going to end up over here. Now if the slow pointer takes 1 more jump, slow pointer is going to end up over here. Again what would happen is that now again fast pointer is going to take 2 more jumps. So fast pointer is going to end up over here. Slow pointer is going to take 1 more jump. So slow pointer is going to end up over here. Now again fast pointer is going to take 2 more jumps. So now fast pointer ends up over here where slow pointer already was. Again we find the similarity, which means we detected the cycle, and we can return true that yes, there exists cycle in this linked list. So this is the most beautiful way to solve this problem, where you simply use 2 pointers of fast and slow pointer and you immediately find the solution. If we see time complexity, in this case the time complexity is going to be big O of n, because we are not doing any more work than that. If we see space complexity, this is the most critical part. Apart from using couple of pointers, we are not using any additional space. So space complexity is also constant, and this will make your interviewer giggle because he just found the right candidate. So let's see the coding solution for linked list cycle problem. So first we are going to check for an edge case that if the given head is equal to null, we are going to return false immediately, because that's like the simplest thing to do. Now if that is not the case, we are going to initialize 2 values, fast pointer and slow pointer, and we are going to see for the condition that while slow is not equal to fast, fast pointer is keep on going to incrementing and slow pointer is going to keep on incrementing. At the same time, we are also going to check that if the fast pointer is equal to null or fast.next pointer is equal to null, which means we have reached to the end of the linked list and we haven't found the cycle, we can return false immediately, that there is no cycle found. If that is not the case, and if we get out of the loop, which means that we detected a cycle, because we will only get out of the loop when slow and fast pointer comes at the same position. And if that happens, we will return true. So let's try to run this case, and seems like our solution is working. Let's submit this code, and our code runs 100% faster again, because the runtime is again 0 millisecond. I'm not doing anything special. Now let's just move on to the next question, which is, I found this problem to be very unique problem and very good problem. Like I was pretty happy with this problem. I know Some people might like it, some people not like it, but in my opinion everyone should at least go and try to solve this problem at least once, because it's too much fun. I found it hilarious. The problem is a happy number problem. And if we see some of the popular companies who have already asked this, there are companies like Amazon, Google, Facebook, Yahoo, Apple, Bloomberg, ByteDance, Uber, TikTok, Microsoft. So all the top tier companies have asked this question, because this question in my opinion is like awesome problem. Okay, if we see, this is pretty easy problem and this has been liked by a bunch of people. We need to write an algorithm in this problem to determine that if the given number n is a happy number or not. Now, and we are given some definition that what defines a number to be happy. So basically what defines a number to be happy is that starting with any positive integer, replace the number by the sum of squares of its digits. I'll explain you what does this mean. Next thing it says that repeat this process until we find that the number equals to 1, or the loop endlessly runs in a cycle that does not include 1. So if we do this first procedure, there are two possibilities, that eventually it would lead us to a value where the total value becomes 1, or eventually it would lead us to a scenario where it's keep on going in circles again and again and again, and we would never be able to reach to this value number 1. So if we are stuck inside the loop, which means number is not happy. If we are able to reach to this value number 1, which means number is happy. And this is what we need to do, whether to determine whether the number is happy or not. Okay, so now let's see some examples to know that what if the number is happy or not. Suppose we are given a number n is equal to 19. So now let's try to read the first line, what it is asking us to say. Basically the first line defines that we need to check that whether starting from any positive integer, replace the number by the sum of its squares of its digits. So what are the digits of this n? It's 1 and 9. So what we are going to do is we are going to replace this 19 with the sum of its square of its digits. So digits are 1 and 9. Square of 1 is 1 square plus 9 square. Sum of these two we need to do. So this is going to be 1 plus 9 square is going to be 81. So this answer is going to be 82. So in the next iteration, we are now going to have the value 82. Again, let's repeat the same process. So 8 square plus 2 square. So this is going to be 64 plus 4. So this is going to be 68. Okay. Again, let's repeat the same process. So 68. Now again, 6 square plus 8 square. So this value is going to be 36 plus 64. So this value is going to lead us to value number 100. Again, let's repeat the same process. So 100. So now we are going to do 1 square plus 0 square plus 0 square. So now this value is going to end up at position number 1. Now, since this is position number 1, even if we do the next value for this 1, the answer is going to be 1, and this is going to remain as it is. And the last condition over here defines that those numbers for which process ends in 1 are happy, which means we can determine that this number 19 is happy. Same way we can determine that this number 82 is also happy, because if we are given number 82 as the input over here, again we would repeat the same process. It would lead us to value number 1, and that is going to be the answer. So in this case, our original input was 19, so let's just keep it as 19. 19 is a happy number, so we can return true in this case. This is the whole method and this is the whole procedure. Now you know that for this scenario this value is true. Let's try to take one more example where the answer is not going to be true. Now suppose we are given the number n is equal to 2. The 2 square is going to be value number 4. Okay, so next iteration is going to be 4. Again for 4 square is going to be value number 16. So again for 16, now the value is going to be 1 square plus 6 square, so that is going to be 37. Again for the value number 37, it's going to be 9 plus 49, that is going to become the value of 58. Again for 58, it is going to be 5 square, so 25 plus 8 square, 64. Now this time the total is going to become 89. Again for 89, it's going to be 8 square to be 64 plus 9 square to be 81. So the total value is going to be 145. Again for 145, we are going to do 1 square plus 4 square plus 5 square. So it's going to be 1 plus 16 plus 25. So the total is going to be 42. Again for 42, it is going to be 4 square plus 2 square. So that is going to be 16 plus 4. So the total is going to be 20. Again for value number 20, we are going to do 2 square plus 0 square. So 2 square plus 0 square is actually going to give us the value of 4. The question is, have we seen 4 before? Yes, 4 is actually present right over here. So even if from 4, if we keep on repeating the same process, what would happen is that the next value we would get is going to be 16. The value further that is going to be 37. Eventually it would keep on leading us to this value number 4, and then we would be stuck inside this loop and we won't be able to get out. So basically we would never be able to come up with a value that is equal to 1, and this number is always going to be not a happy number. Now if let's just take a step back, what we did is that starting from n is equal to value number 2, if we just plot all the lines in a sequence, how would those lines look like? And from this value 20, again this is going to point to value number 4. So this is how it will look like. So now what we did is that from this starting value, we know the formula on how to generate all of these values. Initially we are not given these as any like linked list or an array, but this is a sequence that is derived from this value number 2 based on the mathematical equation we are told to do the square of its digits and the sum of that. Eventually this leads to a position where we are coming back to the same position, which means we are detecting a cycle. Now you know, the moment we detect a cycle, there are actually two ways to solve this problem. First way is that we actually keep track of all of these values inside our hash set, and inside the hash set we will see that whether this value number 4 has been visited before or not before adding that to our chain. If it has been visited, we can clearly detect that there is a cycle found, and then we can return that this is not a happy number immediately because we identify a cycle. But with this hash set approach, the space complexity in this approach would end up at big O of n again. So this is not what we wanted, and we want to do something better. And this is what your interviewer is going to ask you, that can you do this without using a hash set? And again, for this problem, since this is a detecting cycle problem, we are going to use one of the most beautiful concepts that we learned recently, and that is the fast and slow pointer concept, where fast pointer is going to do 2 iterations at a time and slow pointer is going to do 1 iteration at a time. And the moment fast pointer and slow pointer ends up at the same position, we can determine that the cycle has been detected. If that is not the case, and somehow we found that the fast pointer ends up at position number 1, or fast dot next position is also 1, if either of these two cases, then the number is happy. If that is not the case, and if fast is equal to slow, then cycle is detected, which means the number is not happy. And this is what we need to prove. So let's just see a demo of fast and slow pointer in action. After first iteration, fast pointer would end up over here, slow pointer would end up over here. Again, fast pointer would end up over here. Now this time again, slow pointer would end up over here. Now this is where slow pointer would end up. This is where fast pointer would end up. After 145, the fast pointer would end up over here and slow pointer would have been here. Now again, from this position, fast pointer would again come back to this position number 4. And meanwhile slow pointer would be here. After 2 iterations, this is where the fast pointer would be. Let me clean this up a bit so to make things more readable, and at the same time the slow pointer is going to be located over here. After 2 iterations, fast pointer would be over here, and now slow pointer would be over here. After again that, fast pointer would end up at the same position where slow pointer is, which means that a cycle has been detected, and we can immediately say that this is not a happy number for this value number 2, and this is the solution we can return. Again, we can repeat the same process for this value number 19, because even if we see for 19, let's just try to create a similar plot for value number 19. Okay, so this is the plot for value number 19. Currently this is the fast pointer, this is the slow pointer. Fast pointer jumps 2 places, slow pointer jumps 1 place. Again, fast pointer jumps 2 places. Fast pointer is currently located at position number 1. Meanwhile slow pointer is here, but that doesn't matter because we find fast pointer is equal to 1, which means number is happy, which means we can return true that the number is happy, and this is what we want. So see how beautifully we solve this problem. And now you would ask that how can we actually generate this sequence? Well, in the code, what we will simply do is that we can actually create a helper method whose entire task is that if you give a number as the input, it would be able to generate that what would be the next value. And this is pretty easy to do because this is just a simple few mathematical steps we have to follow. So that I'll show you in the code how we are able to do it. And then all it becomes is to find that whether for the sequence that we are making, whether we are reached to the value 1, that is the end value, or are we detecting a cycle. And this is how the power of 2 pointers are being in place, and you are able to solve this problem pretty easily. If we see time and space complexity, in this case the time complexity is actually going to be big O of n, and the space complexity, the most beautiful thing, big O of 1, because we use the fast and slow pointer method, or we can also call it the hare and tortoise method, or we can also I like to call this as Shifu and Oogway method. So whatever you want to call it, use it in your interview. Your interviewer is going to be impressed. And let's move on to the code. Now let's see the coding solution for the happy number LeetCode problem. First of all, we are going to create a method that would allow us to find the total sum for any given integers. So what this method is going to do is that this is going to calculate that what is the total sum of the square of all the digits that are present inside our given number n, and in the end this is going to return the total sum. So this total sum would be the input for the next element. If I want to give it through the example, suppose if we give the 19 as the input for this get next method, this would return us the total sum of value as 82, and the next input would be 82, so we would get value as 68. So this is just for explanation. Now let's just get back to our main method, where we are again going to have 2 pointers, fast pointer and slow pointer. And the fast pointer is simply going to keep running with the first element. Meanwhile, fast runner is going to move 2 steps at a time. Now we are going to run a while loop, and the conditions are that while the fast pointer is not equal to null, or if the slow pointer and fast pointer ends up at the same position. If that is the case, then we will keep on running, where we are going to call the get next helper method that we created, and we are going to keep on providing the value of the slow runner or the fast runner, and we are keep on going to update the value. The moment we get out of the loop, either of the two things could have happened. It could have been possible that fast runner found the value to be 1, or fast runner and slow runner ended up at the same position. So if the fast runner value is equal to 1, we would have returned true. If that is not the case, we would have returned false. And this is the whole solution for the happy number problem. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And again, our code runs pretty efficiently compared to a lot of other solutions. And I hope this solution made sense. Hello friends, so today we are going to learn about breadth first search. This has to be one of the most popular coding pattern out there, and in my opinion this coding pattern has to be asked in probably millions of interviews all across world, and there is a very simple reason for that. Breadth first search solves some of the most common real life problems that we see in our day-to-day life, and using this technique there are actually bunch of different really popular products and companies are completely built upon. So that is why interviewers love asking breadth first search type of questions. Second thing is that breadth first search is also referred as BFS, and throughout this problem we would be interchanging between the names of breadth first search or BFS. Now the flow of this video is going to be that first we are going to have an overview of what this breadth first search technique is, and in this overview we will also see that what type of data structures use this breadth first search technique. Next we are going to see that what does a typical workflow looks like for any single breadth first search problem. In the end, we are going to see 3 different real life examples, and these examples that I have chosen, they are really popular example, plus they solve some real life scenario or some real life problem. And I'm going to explain you the problem statement. I'm also going to explain you the different solutions, and I'm also going to show you the Java code for all of the solutions that I'm going to explain. So this is going to be really action packed video in my opinion. This is going to be much more informative compared to my other coding pattern videos, because this coding pattern in itself is so much more popular. So I highly encourage you to pay some extra attention and learn this technique as efficiently as possible, because this can have tremendous rewards for you. Now, if we want to see the overview of breadth first search, basically we have to understand that where breadth first search technique applies. It typically applies amongst 2 ways. First one is a tree data structure, and second one is a graph data structure. And the way we can use this breadth first search technique in tree or graph data structure is that breadth first search is basically a mechanism to traverse over or to go over all the nodes in the breadth for in any given tree or graph data structure. That is it. That is the whole point of having a breadth first search, that this technique allows you to iterate over any single tree or any single graph, but in that iteration you would be able to find some meaningful value, that and you would be able to solve the problem that you are actually aspiring to solve. So first let's see the overview and the typical flow of breadth first search. For that I'm going to use one tree and one graph example. So first I have decided to show you the BFS on a given tree. Now in this example we are using a binary tree. So what binary tree means is that every single node has at most 2 children, nothing more than that. They can have less than 2 children, but they cannot have more than 2 children. Now I mentioned that BFS is simply a way to traverse over the given tree, and the logic we are going to apply is that because this is a tree, we are going to start iterating from the root node, and in the root node first we will visit the root node, then we would visit the children of the root node before visiting the grandchildren of this root node. So we are going to visit children first, then for those children again we are going to visit their children first, and even for those children we are going to visit their children first. So every single time we are iterating level by level inside any given breadth first search for a tree traversal. Again, let me repeat that we are going to iterate in terms of level. So first we are going to iterate over the level 0. In the first iteration we are at the root position. So I already mentioned that the path is going to look like this, that first we visit value number A, then we are going to visit its children. So currently the children are B and C. So then we are going to visit nodes B and C after visiting node A. From this B and C, for B currently we have the children D and E, so that we are going to visit after visiting C. So for B we are going to visit children D, and also we are going to visit the children E. Again for C it has children F and G. So again from E we are going to visit to node F, and then we are going to visit node G. In the end, for this particular E, it has also a child called H that we are going to visit in the last. And if you notice that first we visited the first level that only had one node, second level had 2 nodes, third level had 4 nodes. So we visited all 4 nodes, and in the end we visited the last level, and that is where the position H is located. Now you must be wondering that how we have been able to achieve this. Well, I will explain you that how any typical computer is going to do this, but first let's see an example for a graph as well. So let me quickly draw a graph and we will see a BFS example, and then we will see that how to implement it like a typical common workflow for a BFS. Okay, now for this example we would see that how a BFS is going to work for a given graph. Now unlike tree, graph does not have a root node, which means we can start our BFS from any single node. And again, just like tree, the logic we are going to use is that inside the tree we were actually iterating the children of the any given node before visiting its grandchildren. Well, in the graph we don't have a children, but we actually have neighbors. So again we are going to apply the same logic, that we are going to iterate the neighbor of any particular node before iterating their neighbors. So again we are going to go level by level in this fashion. This is just for an example purposes, but there is one key thing that we have to take care in graph that we were not concerned about in a tree. So I'm going to explain that in the example. Suppose we start our traversal from this value number 3. Okay, we can take any arbitrary value. I'm just taking 3 for an example. So first node we are visiting is going to be node number 3. Now we are going to visit the children of this 3. So children of this 3 is 5 and 4. So we are going to visit node number 5 and node number 4. We can visit this in any order. There is no particular way, but just for simplicity, I'm just going to write down one of the possible path. Now for this 5, there are no children or no neighbor. So because 5 does not have any neighbors, we would not need to iterate over any further, but this 4 already has some neighbor. So now from this position number 4, okay, first neighbor is 6 and second neighbor is 2. So we are going to visit 6 and 2. Again 6 does not have any neighbor, so we are not concerned about this one, but for this 2 it has 2 neighbors, 1 and 0. So again let's try to do this. So 2 visits node 1 and again node 0. Now what would happen at this position node 1? How many neighbors does 1 have? Well, 1 also has 2 neighbors. First one is node number 2 and second one is node number 0. So again, if I try to visit the neighbors of 1, what is going to happen is that I'm going to visit node 0 and also node 2. But now what happened is that from this 2, we visiting after visiting multiple elements, we came back at the same position. So again, from the 0, rather than creating a new loop to 1, we can actually create a new loop to 2 over here, which means we are actually running in circles because there exists a loop in this case. And remember, trees cannot have loops, but graphs can have loops, and that causes a big problem here. So whenever we are dealing with graphs, we will always have to make sure that we find a way to keep track of all the nodes that we have visited already. And in order to keep track of visited nodes, typically a hash set is a great example. And most of the time, whenever you are dealing with a graph problem, and either you are using breadth first search, so this is one of the most popular technique. Another technique is a depth first search that I'm going to explain in the future videos. But in either cases, you have to make sure that you take care of the visited node, because you do not want to end up in an infinite loop cycle. So now again, let's just go back and let's just mark all the nodes that we have visited. So 3 we already visited, same way we visited 5 and 4 and 6 and 2. So all of these nodes we have visited so far, and now let's repeat the same process. So from this 2, we have the 2 neighbors, 1 and 0. So 1 and 0 are the neighbors. And remember, all the nodes that I just mentioned that we have visited, we are going to put them in a hash set. Okay. So hash set would be able to quickly tell us whether any node has been visited or not, because it operates in big O of 1 time complexity in order to find whether any element exists inside the hash set or not. And that is why it is a great way to use visited hash set. Now again, coming back to our BFS pattern. So from this 1, we have 2 more possibilities, 0 and 2, but 2 is already visited inside the hash set, so we are not going to visit 2. And 0 we already visited. Now 1 has also been visited. Now from the 0, we only have 2 neighbors, 2 and 1, but since both are visited, we cannot go further anywhere, and we can determine that we have actually reached to the end of our traversal for our graph. And this is how the breadth first search is going to work inside a graph. Now you understand that how does a typical flow works, but can you explain that how we would be able to actually implement this breadth first search? What is the technique we are going to use? You already know that this can be used in a tree, a graph kind of a problem, but we need some way to keep track of all the nodes. So one way, we are entering the current node that we are going through in the BFS, and we will also have to keep track of its neighbors inside graph. So the best way to use a BFS is that we can actually implement it using a queue. And what this queue is going to allow us is that it is going to allow us to keep track of all the neighbors of any particular root item, because they would be still placed in a queue. And remember, queue has a wonderful property, and that is that first in, first out. So the first children that came in would be the first children coming out, and if they also have subsequent children or neighbor, they would still be inside the queue. Now let me give you a quick demo on how a queue would work, and we are going to use the same example. So let me clean this up a bit. So for the same example, as mentioned, we are going to use a queue. And inside the queue, what we are going to do is, first imagine we are starting our iteration from value number 3. So we are going to populate the queue with value number 3. Now our BFS function is going to do 2 things. First thing it is going to do is check that whether queue has any element or not. Queue has element 3. So now we have this value number 3 that we haven't taken care of. And also remember, we are also going to use a hash set that is a given fact. Okay. So for all the values that we have already visited, I'm just going to mark them in this graph. Now, first thing we are going to do is, for this value number 3, we are going to check that whether 3 has any neighbors or not. And 3 does have 2 neighbors. So first neighbor is this value number 5, and second neighbor is value number 4. So the moment we identify existing neighbor for any element, we are going to add them to our queue. So awesome, let's just add them 4 and 5. And also at the same time we are going to check inside the hash set. So since they were not visited, that is why I added them in the queue. Okay, so first we would check whether they exist in the hash set. If they don't exist, then we add them to the queue. Now we have visited all the neighbors of the value number 3. There are no other neighbors that exist, so we can mark 3 as visited. The moment we mark 3 as visited, we are going to also pop it out of the queue. So now our queue is only going to have 2 elements, and that is 4 and 5. Now 3 has already been taken care of, and 3 was one of the first elements that we visited. Okay, now next we are going to check whether queue has any element or not. Queue has element number 4. So again we are going to repeat the same process. Does 4 have any neighbors? So 4 has 2 neighbors. First neighbor is 6, second neighbor is 3. But we check in the hash set, 3 is already visited, so we do not visit 3 again. But 6 has not been visited, so we will add entry 6 over here. Again we repeat the same thing. We pop 4 out and we move all the values. Okay, so currently again values that are there are 5 and 6. And also I forgot that 4 also has the neighbor 2. So apart from 6, 2 is also one of the neighbors, and after that we would pop 4 out, and from 3 we would visit value number 4. Okay, again we repeat the same thing for 5. 5 does not have any neighbors, which means we can pop 5 out, mark it as visited, and we be done with it. Same we are going to do with 6. Okay, so after 3 4 we are going to visit 5 and 6, and they are all visited, and we are going to dequeue them as well. So currently inside our queue, the only value we are going to have is going to be value number 2. For this value number 2, first, okay, neighbor 4 already visited, no need to visit. Neighbor 1 not visited, so add it over here. Neighbor 0 not visited, so add it over here. After all visiting all the nodes, remove 2. So 2 has been removed. Okay, awesome. Now 2 has been added over here, and then again repeat the same process and also mark 2 as visited. Again repeat the same process for 1 and 0. So since 1 has neighbor 0, so we are going to add 0 over here. But and also at the same time we are going to check the hash set. Hash set already has 0, so we would not add it over here. My mistake. But we would not add, and then we would dequeue 1, and then in the end we would dequeue 0. So simply we have the path 2, 1 and 0, and this is it. This is the whole solution that we need to take care of. And this is how you would implement a breadth first search for a graph. Same technique is going to be applied for a tree as well. The only difference is that in the tree we don't care about the hash set, because typically you would not encounter inside the infinite loops. But the thing is, inside the tree, depending on the question, sometimes you might have to use hash set, but in the graph you will have to use it. This is a must for a graph. For a tree, this is optional, so take care of this one. Now let's see the first example, and the first example is that we will try to find the shortest path between any two nodes. Now notice that we are given an undirected and unweighted graph in this example, and we are going to use the same example. Suppose we are told that find the shortest distance between 2 and 5 node. Okay, so we need to find the shortest distance between node 2 and node 5. So the quickest way to do it is that we already know that breadth first search is a great way to find the distance, to iterate over the given graph. Also, breadth first search can be a great way to find the path between any two nodes. And how it is able to achieve it is that we are going to start iterating from 2, and we will try to see that whether we can go in any direction that leads us to the value that ends up at value number 5. And if it can, we are going to mark that path, and we will try to see that whether there exists any alternate path that provides us the better answer. If there does not exist the alternate path, we are going to mark this path as the most optimal path and return that as the answer. So let's try to see how we are going to able to be solve it. We already know how to apply BFS using a queue. So awesome, we are going to use a queue. At the same time, we are also going to use a hash set to mark all the visited nodes. Starting from 2, we are okay. So we add value 2 over here. Again, neighbors 1, 0 and 4. So again, add all the neighbors 1, 0 and 4. Now 5 is still not found. So keep going, pop out 2, and then again repeat the same process. So for 1 and 0, it would not lead us to any answer. So again, we would eventually pop them out. 4 is the immediate neighbor, and again we would pop 4 out. From 4 we would be able to go to value number 3 and 6. 6 is not going to lead us anywhere, but this 3 is going to lead us to value number 5, and we at the same time are going to plot the path. So from 2 we had we have 3 possibilities. First possibility is value number 1, second one was 0, and third one was 4. Again from 4 we had 2 possibility. 4 had the value as 6 and 3, and from this 3 we had the possibility of value number 5. I'm just explaining this tree from this graph just for pictorial representation. Don't think that we are going to create a new tree like that, but I'm just showing you that how different paths are being navigated using breadth first search. And the moment we identify the value number 5, we can actually have a function that tracks the previous neighbor from where 5 got it, and then we can keep track of, and we can actually plot a path. So in this case, the path we are going to choose is going to be 2 to 4, then 4 to 3, and 3 to 5. Let's see in our example, the path is going to be 2 to 4, 4 to 3, and 3 to 5, and this is going to be the shortest path between two nodes. Say for an example, if it happens that there exists another path as well, and suppose that path is that even from this 6 we have say for an example one more node, let's just say 7, and then this 7 is also pointing towards 5. Now what would happen is that there are two paths that exist that leads us from value number 2 to value number 5. First path is that 2, 4, 3, and 5. Second path is 2, 4, 6, 7, and 5. But in both the cases we need to find the shortest path, and that is quite simple to find. We would only check that how many number of neighbor jumps or hops we need to take in order to reach from value number 2 to value number 5, and this would allow us the shortest path. Now let me get back to the original topic when I mentioned that the breadth first search is so popular and why it is used in so many bunch of different companies. Because what you did right now is actually one of the use cases that typically Google Maps does it for you. So see, in Google Maps, typically it will you would give it 2 points, and the Google Maps would be able to find the distance between those 2 points. The problem is called number of connected components in an undirected graph. And if we see some of the popular companies who have already asked this question, there are companies like TikTok, Amazon, Google, Facebook, LinkedIn, Microsoft, DoorDash, and Twitter. So this problem has been really popular amongst topmost companies, and let's see that what the problem statement is trying to convey. Basically, this is a LeetCode medium problem and also very well-liked problem. It says that we have a graph of n nodes that we are already given, and we are basically given the edges that defines that there is a connection existing between those two nodes for any given graph. Now, based on that, we need to indicate that how many number of connected components are present inside the graph. So let's try to understand this with an example. In this case, currently we have 5 nodes. So basically we are given an n is equal to 5 as the number that defines that there are 5 nodes. We are also given these edges. So we would have given 3 entries, and the first entry is going to be 1 to 2, second entry is going to be 1 to 3, and third entry is going to be 4 to 5. Now, based on these two items, we need to define that how many number of connected components that exist, which in this case, we can see that this is the first connected component because these 3 nodes are connected with each other. And same way, this is the second connected components. So in this example, for this given input, we can define that there exist 2 connected components, and we need to return 2 as the answer. So this is the whole ask of the problem. Let's try to understand this with one more example. Suppose in this case, currently we are given n is equal to 7, and we are given all of these different edges. Now in this example, we can clearly see that there exist 4 different connected components, and those 4 components are these, that this is the first one, this is the second one, this is the third one, and though this 7 is not connected with any other node, still this is a connected component in itself because it's connected with itself. So in this case, in total, since we have 4 connected components, we need to return 4 as the answer. Now let's see that what is going to be the strategy to solve this problem. Suppose we take the same example as the input, and we will try to see that what should be the answer. Now again, remember, we are given 2 things. First, we are given n is equal to 7, so that we know for sure there exist 7 nodes, and we are given all of these 5 edges. Now, based on these number of nodes and edges, we can clearly do one simple thing, and that is to treat this as a graph problem, because that what it is. Basically, we know that a graph is comprised of two items. First one is a node and second one is an edge, and which we are just told in plain English that these are the two entities we are given. So we are going to treat this one as a graph. Now the aim is to find connected components, which means from any single edge or any single node, we will need to define that how many other nodes that particular node is connected with. And if we keep on repeating the same process, and the moment we find the connected nodes, we can eliminate all of those nodes. So, and repeat the process for all the 7 nodes that are given, we would be able to find the number of connected components quite easily. And the technique we are going to use over here is the one of the most popular technique in the entire coding industry, and that is called breadth first search. And how we are going to use BFS? Well, we already know that in order to use BFS, we will have to use queue, and we will also have to use number of visited nodes that we have already visited. So using these two items, we are going to make our lives so much easier, and let me just walk you through the solution. First thing we are going to do is we are going to we can start from any node, because this is a graph. There is no particular definition that we need to start from here or we need to start from here. Say for simplicity, we start from this node number 0. So we are going to have our queue. Now inside our queue, currently we don't have any elements, and we also have our visited hash set. We can also use visited array. I'm just giving you example of visited hash set. Either way, we are going to have a mechanism to keep track of all the numbers or all the nodes that we have visited so far. So this is our visited hash set, and this one is our queue. Okay. Now first we start with node number 0. Now for node number 0, we are going to mark this one as 0. So we are going to enqueue with 0. Now we are also going to mark 0 as visited. Okay. And we are also going to have one more number that is called the number of connected components. So let me just mark this one as counter. Okay. And currently the initial counter value is going to be 0. But since we found one node, we know for sure that there exists at least one connected component, because it could be connected to itself. So in that case, we are going to increase the number by 1. Okay. Now for this particular 0, we are going to run BFS, and by running BFS, what we would be able to do is that we would be able to go through all the neighbors that the 0 is connected with, and then mark all of them in the visited hash set. So even in the future, for this n is equal to 7, if we come back to the same node, if that node has already been visited, we will just simply skip over it. So let's just do that. Now for this 0, it has two neighbors. First neighbor is neighbor 2 and neighbor 1. Currently both are not visited. So let's just add entry 0, 1 and 2 over here. And then we will mark 1 and 2 inside our queue, because we need to do something with that. Currently the count is still going to be 1 because all the nodes are connected. Now we pop 0 out and we do the same process with 1. Currently for the value number 1, 1 is also visited. So since 1 is already been visited, we do not need to do anything with 1, and we can simply pop that one out. Again, 2 is also visited, so we do not need to do anything, and we can pop it out. Now after iterating or after doing the BFS starting with the node 0, we have simply eliminated node 2, node 1 and node 0 by itself, and so far the count has been 1, and we have all of these 3 nodes in our visited hash set. But we know that there are still 7 nodes that we have to take care of. So we are going to iteratively go over every single one of them. Initially we started with 0, so we got rid of it. Let's just start with 1. Again for 1, since 1 has already been visited, we do not need to increase the counter and move on to the next value. Again 2 has also been visited, so we do not need to increase the counter and move on to the next value. So all of this entire connected component has been taken care of. Moving on to the next value, starting at position number 3. Since 3 has not been visited, adding 3 over here, adding 3 in the queue as well, going through all the neighbors of 3. Currently 3 only has one neighbor, and that is value number 5. 5 is not being visited, and also since we find a new element 3, I forgot to add the increment the count. So now the number of connected components we have found so far is going to be 2. I forgot that, but this is important. Now going back, the currently 3 is connected with 5. 5 has not been visited. marking 5 as visited, at the same time adding 5 inside our queue to visit further neighbors of 5. Now 3 does not have any more neighbors, which means we can get 3 out or dequeue 3, and then we are going to have value number 5 remaining. 5 has one neighbor, that is 3, but since 3 has already been visited, we cannot do anything with that. So we are also going to get rid of 5, and 5 has also been taken out. This means that currently we do not have any elements inside our BFS function. Now moving on, currently we went through 0, 1, 2 and 3. Now we need to go through value number 4, because there are 7 elements inside our given input. For even again repeating the same process for value number 4, currently 4 has not been visited, so we will mark value number 4 as visited. At the same time, we are going to put 4 inside our queue. We are going to go through the neighbor of 4 current, and we are also going to increase the count. I always forget to increase the count, which is the most popular thing, that which is the most important thing asked in this problem. But anyways, now going back for value number 6, it has not been visited, so we are going to add value number 6 over here. At the same time, add value number 6 over here. Now we iterated over all the neighbors of 4, so we are going to dequeue 4. After dequeuing, currently there is only element number 6 staying in. 6 currently has one neighbor, that is value number 4, but since 4 has already been visited, we do not need to add it to our queue, and then eventually we would pop out 6 as well. Now what we have done is that currently, in order to find these 3 connected components, we already visited nodes 0, 1, 2, 3, 4, 5 and 6, and all of these nodes are visited. Now in the end, we are going to be at the position number 7. Since for position number 7, this node has not been visited, which means we need to increase the counter. So currently the counter is going to be of value number 4. Now we are going to add 7 to our list of visited nodes, and also we are going to mark 7 inside our queue. Since 7 does not have any neighbors, which means we can pop 7 out immediately, and now our queue is empty. We have already iterated over all the number of 7 nodes that were given as the input, and we are basically done with the problem. So in the end, whatever the value that has been stored inside this count variable is the answer we need to return. So simply at the end, we can return that there are 4 connected components in this problem, and this is the complete solution. Now if you see how beautifully we were able to come up with the solution, and in this case, if you see time and space complexity, the time complexity is going to be big O of V plus E, where V defines the vertices or nodes, and the E defines edges, because that is the time complexity to run the BFS function and go over the entire given input array. So this time complexity is pretty good. If we see space complexity, now space complexity is also going to be big O of V, because we are using the additional data structure of Q and also a hash set or array. There are 2 ways to do it. I typically like to use hash set, but you can also use an array as well. Both would work equally fine. In either case, this is a very good time and space complexity. And remember, one of the most important concept is inside the graph theory, the breadth first search allowed us to solve this problem smoothly in a beautiful manner. Here is the coding solution for number of connected components in an undirected graph, where first of all, we are given in the input the value n, and we are also given a 2 by 2 array called edges. So first thing we are going to do is create an adjacency list and to create a graph like structure. So this is going to allow us to iterate over graph in a much easier fashion, which this process is doing, where we are running across every single edge and every single node and plotting them on the graph. After that, we are going to have our Boolean array called visited, and we are also going to have a value called count that initially we are going to set it up as 0. We are going to run our for loop starting from value 0 to the total number of n that is given in the input. And then inside the for loop, first thing we are going to check is that the current ith position, if that is not visited, then we are going to call our BFS function, and at the same time we are going to note it as the new connected component found, and we are going to increment the number of count. Now let's see that what is going to happen in our helper method BFS, where we are taking a graph as the input. We are also taking the number of nodes that have been visited so far, and we are also using the starting pointer from which we are entering inside this given graph. So first of all, we are going to initialize our cube. We are also going to have a visited array that we are going to mark as true for the current node that we are visited. And while there are no entries inside the queue, first of all, we are going to pop the last added element inside the queue, visit every single neighbor of that node, and for all the neighbors that has not been visited, we are going to mark them as visited, and we are going to add it to our existing queue. And by doing this operation, we would be simply running through every single connected component. So suppose here I give you like 0 as the input, then through this BFS method, 0, 1 and 2, all three nodes would be marked visited because they all are connected. And this is what this operation is doing. And in the end, after this for loop ends in our main method, we simply need to return the count that we have found that would allow us to find the number of connected components. Let's try to run this code. And our solution works perfectly fine. Let's submit the code. And our code runs decently efficiently. And don't worry about that you are not being able to see the code. I'm going to put this code inside the GitHub, so you would be able to find it quite easily from there. So the lead code problem we are going to explain is going to be binary tree zigzag level order traversal. This is a really popular problem, and this has been asked in some of the top tier companies such as Amazon, Bloomberg, Microsoft, Facebook, Apple, LinkedIn, Google, Samsung, Goldman Sachs, and TikTok. So that is why I'm paying my utmost attention. I highly urge you to pay your attention for this problem as well. If we see that this is a lead code medium problem and also very well like problem. Now in this problem, we are given the root of a binary tree, which means a binary tree means that any single parent can have at most 2 children, nothing more than that. So now we have the root of this binary tree, and now we need to return the zigzag level order traversal from its nodes values. So what does a zigzag level order traversal means? So first of all, before understanding the zigzag level order traversal, let's understand what does a level order traversal means. Level order traversal simply means that first we go through the first level, that is level 0, then level 1, then level 2. So if we see the level order traversal, first we would it go through value number 3, then second level, so that is value number 9 and 20, and then the third level, that is 15 and 7. But since in this case the level order traversal that we were making was pretty simple, we were going from left to right. So we went from here, we went to left to right, again from here we went from left to right. But in this case we are making our lives easier and we are going in the zigzag fashion because that is the current trend. And zigzag fashion is that first we start over here from left to right from the root node, then we go in the zigzag fashion. So we go like this, and now again we repeat the zigzag pattern, and now we go from left to right again. So for one level we go from left to right, next level we go from right to left, and again next level we go from left to right, and we keep on repeating the same process. So in this example, if you see, first we went through level 3 left to right, this was the value. Second we went through the right to left, so 20 and 9. So from after 3 we visited 20 and 9, and then we went through 15 and 7, and let's see what would be the solution for this problem. Okay, suppose this is the input we are given. Now first let's see what is the level order traversal going to be. First we are going to visit value number 1, then we are going to visit in this fashion. So the value is going to be 3 and 2, then again from this fashion, so value is going to be 4, 5, 6, and then again from this fashion, so the 8 and 7. This is going to be the answer for sure. We already know that. But how we are going to come up with the answer? In order to come up with the zigzag level, first we need to go through the simple level. How to go through simple level order traversal? Well, for what we are doing in a simple level order traversal is that we are iterating the parent, then we are iterating its child before iterating its grandchild. So in this case, first we are going to we are at this place, we are going to iterate over its child. After iterating both children, we are going to iterate its grandchildren or the children of these children. So first we would be covering this level, Then after covering this level, we would be going through the children of these nodes, and so going in this fashion, and again repeating the same process with this one. And this can be achieved using breadth first search because it's pretty simple to do, and this is how how traversal is done in trees using breadth first search. That is a level order traversal. So even in this case, we are going to use the breadth first search to run in a simple level. But how do we use breadth first search? Well, from our experience, we know that in order to use breadth first search, we need two items. We need a queue and we need a visited hash set. But the thing is, we only need visited hash set in a graph kind of a problem where there is an issue of us running in an infinite loop. There is no issue of us running in an infinite loop inside a tree. So we are not concerned about using a graph in this case. We are only going to use a queue. And currently I'm just showing you how to do a level order traversal, and then we will do zigzag level order traversal. So first let's just see the level order traversal. For that, we are first of all going to start at the root position and we are going to populate that value inside our queue. So this is currently value number 1. Now we are going to visit the children of 1 before visiting the grandchildren of 1. This is the whole logic of the BFS, that we are going to visit the children before visiting the grandchildren. So who are the children? Obviously 2 and 3. Again, we are going to add values 2 and 3 here because it has 2 children and we are going to mark them. Now we visited all the children of value number 1. So we are going to pop value number 1 out and we are going to put it in the answer, that we traversed this part already and now we only have values 2 and 3 inside the input. Now again for 2 and 3, 2 has children that we haven't iterated over. So who are the children of 2? 4 and 5. Mark them here, and same way get rid of 2. So 2 has been taken out, and now currently the entries are 3, 4 and 5 inside our queue. 3, 4 and 5. Again 3 can be kicked out by adding 6 at the end of the queue. We added 6 at the end of the queue. Awesome. Now 3 is also out. Currently the entries are 4, 5 and 6. Now even for the values 4, 5 and 6, starting at position number 4, it does not have any child. So 4 can be kicked out without any repercussion. 5 currently has a child 7. So adding 7 at the end and getting rid of 5. So we can put 5 over here. Again values are 6 and 7 in place. Again for value number 6, it has a child called 8, adding 8 in the end and getting rid of 6. And now after that there are only 2 values left, 7 and 8. Currently 7 does not have a child, so we can get 7 out, and also 8 does not have a child, so we can also get 8 out, and this would be the solution. But in this problem what we did is we went in the normal level order traversal, not the zigzag level order traversal. So let's see how can we make zigzag level order traversal possible. Currently what the concept we are using inside the queue is, currently we are using the first in first out principle that gave us the level order traversal. But what happens is that when we move from left to right, this concept is absolutely true, that we can get we can have like first in first out, and that would give us the proper level order traversal. But when it comes to reversing, imagine that in this case, rather than getting 2, since 2 was already inside the loop before value number 3, if we pop 3 out before 2, then we would have been able to accomplish our mission. So since in this case we are going in the zigzag fashion, remember zigzag fashion is going to be like this, where on one iteration we are moving from left to right, next iteration we are moving from right to left, and again for the next iteration we would move from left to right, and we would keep on repeating in the alternate fashion till we reach to all the nodes inside the given input. So now let's see that what are some of the adjustments we can make to make our life so much more easier and fix this issue that we were having in the level order traversal. The solution is quite simple, and the solution is that whenever we have to find from left to right, we can use the concept of first in first out. So this first in first out is going to use on these 2 occasions, but when we need to move in the reverse order or right to left, in this case we will have to use the concept of last in first out. because logically what was happening in this case is that logically we were traversing in last in sorry, left to right for every single one of them in the level order traversal. So typically we were going like 2 and 3, but imagine since 3 was last added, if we took the last in first to approach, then inside the solution we would have values such as this one. So 1 is following FIFO, first in first out. So 1 was added first and 1 was removed first. But for this particular position, we are using the concept of last in first out. So even though 2 was in the queue before value number 3, we are going to have 3, that was the last value, come out before the value of 2. So 1, 3 and 2, such like this. Again, we are going to use first in first out for this particular level. So the solution is going to be 4, 5, 6. That is pretty simple. But for these two, again we are going to use LIFO principle, and that is going to give us the answer of 8 and 7. Now if we see this sequence 1, 3, 2, 4, 5, 6, 8, 7, this matches with the original answer we wrote at the beginning, 1, 3, 2, 4, 5, 6, 8, 7, and this is the whole solution. So let me clean this up a bit, walk you through my solution, where we are simply arranging the way we are entering the values inside the key inside the queue and popping the value out of the queue. Okay, so now we are going to have our queue. We are going to add all the entries, and the only simple thing we are going to do is whenever we have to move from right to left, we are going to pop the value at the from the end of the queue rather than popping from the beginning of the queue, because we are flipping between FIFO and LIFO principle. And the one data structure that is capable to do this is actually a DQ data structure in like both Java and Python languages. So you can use either one of them. Okay, so let's start iterating, starting from value number 1. 1 is placed here. Currently 1 has 2 child, 2 and 3. So we are going to mark 2 and 3 in this position. Currently for 1, we are iterating from left to right. So we are going to get the last in first out. So 1 would come out. Now the values are located as 2 and 3. Even for 2 and 3, currently we need to get them out in the zigzag fashion or right to left fashion. So for that, first we are going to pop it from the end. But before popping it from the end, we will first add the children of 2 and 3. So the child of 2 is 4, 5. So let's add 4, 5 here. And child of 3 is 6. Let's add 6 here. After doing that, we are going to pop 3 out first, and then we are going to pop 2 out first. So 3 and 2 has been out because 3 was value before 2. And again for 4, 5, 6, we need to do the same thing, but we need to do in the left to right fashion. So 4, 5, 6 are going to come out as themselves, but before that we are going to iterate through it their children. So 4 currently does not have a child, so we can pop it out without any repercussion. But 5 has a child, the value is 7, and 6 has a child, the value is 8. Again we pop 5 out. So popping 5 out should be simple, and popping 6 out should be simple as well, because we already took care of them. But for value 7 and 8, again we are moving in the right to left direction. So last in value 8 is going to come out first before 7 coming out. And in the end, we would not have any values inside our queue, which means we can get rid of it. And now you see the traversal is being done in the level order and also in the zigzag fashion. And that is the most important fact. And this is how you solve this problem. Again, if we try to see the time and space complexity, the time complexity is going to be big O of V plus E, or vertices plus edges, or nodes plus edges, because we are using our BFS. And space complexity, since in order to use the BFS we will have to use a queue, the space complexity is going to be big O of V, or the number of nodes or number of vertices inside our given tree. And this is the whole solution. Let's see the coding solution for binary tree zigzag level order traversal. So first of all, for this one, we are given the method that to return a list of lists that contains the zigzag level order traversal of the given input tree, and as an input we are given the root node. So first of all, we are going to check for the edge case, that if the given root node is null, we can return an empty new array list immediately. If that is not the case, first we are going to initialize the array list. Inside this array list, first node, we are going to add the root node, and we are going to add a null node as well, and we are also going to use a new tree node linked list to iterate over the given input tree. Now we are going to mark the level list, because every single level is going to contain a different set of answers, and we are going to use this boolean parameter to keep track that whether we need to traverse from left to right or right to left. So is order left is initially set to true, which means currently at the beginning we are moving from left to right. Now inside the while loop we are going to do our BFS function, where if this given boolean is order left is true, which means we are going to use the last in first out and add all the elements inside the level. If that is not the case, then we are going to use the first in first out and also add all the values that are present on that particular level. After adding all the levels, we are simply going to populate our result list based on the level list we have created, and then we are going to initialize a new level list for the next level, and again we are going to change the ordering from left to right to left for the next level. And after repeating the same process again, even for the next level, the ordering is going to be again left to right. In the end, after this BFS operation doing loop ends, we would have our result linked list populated, and we would be able to return that as the answer. So let's try to run the code. Seems like our solution is working as expected. Let's submit the code. And our code runs pretty efficiently compared to a lot of other solutions. And don't worry, I'm going to post the solution of this code inside my GitHub repository that is open to public, so everyone would be able to see that. So the question is number of provinces. This is a LeetCode 547 problem, and this problem has been popular amongst top tier companies. So companies such as Amazon, Bloomberg, Apple, Two Sigma, DoorDash, Goldman Sachs, Google, Uber, they have all asked this problem. So that's why I hope that you pay enough attention to this one. If we see the problem statement defines that there are n cities that we are given, and we are told that some of these cities are connected, some of these cities are not connected. Now if say city A is connected with city B and city B is directly connected with city C, then city A is indirectly connected with city C. So A is connected with B is connected with C. Suppose this is the relationship, then we can define that A is also connected with C. This is what this problem is, the statement is referring to. Now going back, we are given the definition that what a province is. A province is a group of directly or indirectly connected cities and no other cities outside of this group. So suppose we are given cities like A, B, C, D, something like this, and we are given that A is connected with B, B is connected with C, and we can also refer that indirectly A is connected with C as well. Currently this D is not connected with anyone. In this case, we can define that this A, B, C makes a province, and this D by itself, currently since it is not connected, it is not making a province. But suppose we identify that another city E that exists that is connected with city D, then we can define this to be the second province as well. Okay, so now we know that what the problem statement has given us. We are given n cities, and we are given the connection between those cities, and we are also given the definition of what a province is. Now we are given an n cross n matrix, and wherever there is a connection between any two entities, that particular value has been marked as 1. That defines that the ith city and jth city is connected. And if the value is not 1, if the value is 0, which means that those values are not connected. Now based on this given input, we need to define the total number of provinces. This problem is very similar to one of the previous problems we solved, and that is the number of connected components. And how? Let me just quickly show it to you. What we are given is that we are told that we are given a matrix, and inside the matrix, using the values 0 and 1, we are going to define that whether any two values are connected or not. Okay, so suppose the values are A, B, C, D, and here A, B, C, D. Okay, all the values are by default going to be connected with each other, so I'm going to mark it as 1. Suppose, let's just take the same example. So these are all the items we are given. This is true. Based on all of these items, what we are given is that this is actually not a matrix, but actually this is an adjacency matrix, and adjacency matrix is one more way to represent a graph. Since this is one more way to represent a graph, we can, rather than considering these as cities and these are connection between them, let's just try to think of these as nodes and edges, where nodes are the cities and edges are the connection between them. And now this becomes a very simple problem that we can solve using BFS quite easily. And the whole problem statement now becomes is that we need to identify that how many number of connected component exist inside any given graph, and those connected components, we need to return them as the answer. So I have already solved this one in past, but I'm going to quickly show you the solution again. And simply we are going to use breadth first search. For breadth first search, we all know we need two items. First one we need is a queue, and we need some way to keep track of all the visited nodes so far. So let's just do that. I'm going to initialize our queue, and also I'm going to initialize our hash set that is going to keep track of the visited hash set. Okay, so this one is for visited and this one is queue. Now we can start at any given node. So suppose this is the input we are given. Currently nodes are 1, 2, 3. These three cities are connected, and city 4 and 5 is connected. We are also going to mark one more variable called provinces, and initially the value of the provinces is going to be 0. Okay, so currently this is the variable that is going to keep track of the number of provinces we have been able to find so far. Currently the value is 0. Now let's just pick any arbitrary value. So we start with node 1. So let's just run a BFS starting with node number 1. So first we are going to, since 1 has not been visited, we are going to mark as visited because we are visiting it. We are going to add 1 inside our queue. Now the moment we find a value inside a queue, we are going to iterate through its neighbors. Currently 1 has two neighbors, value 2 and value 3. Both value 2 and value 3 are not visited, so we are going to mark them to the number of visited nodes, and we are going to mark 2 and 3 here. Now we iterated over all the neighbors of 1, so we are going to dequeue 1 out, and we are going to remove it from the queue. Now currently we only have values 2 and 3. For value 2, the number of node is 1 and 3 as its neighbor. Both 1 and 3 have been visited, so since they are visited, we are not going to revisit them, and we are going to pop 2 out as well, that stating that we visited all the nodes of 2. And at the same time we are going to pop 3 out as well, since the neighbors of 3, 1 and 2 are already been visited. Also, I forgot one key important thing, and that is that the moment initially when we started iterating through 1 and we found that 1 has a neighbor 2, immediately we needed to add the number of provinces to 1 because we found at least one province. So we would have found one province, and in order to finding that province, we already visited all 3 nodes. So we are going to mark these 3 nodes as visited. Now, since in the input we are already given n is equal to 5, we initially started with n is equal to value number 1 because it was not visited. Now we will start with n is equal to 2, but that has also been visited, so we will simply skip over. N is equal to 3 has also been visited, so we will simply skip over. Last value is n is equal to 4. N is equal to 4 has not been visited, so marking 4 to our visited list, adding 4 to our queue, and now 4 has a neighbor 5. So again, the moment we find a neighbor, we are going to increase the number of provinces to 2. We are going to add 5 to our visited list. We are going to add 5 to our queue, and then we are going to pop 4 out because we visited all the neighbors of 4. But we haven't visited all the neighbors of 5. Currently for 5, since 5 has already been visited, we do not care, but 5's neighbor 4 has also been visited, which means 5, we also visited all the neighbors of 5. So now we get rid of 5. Now initially for this n is equal to 5, we had gone through 1 to 4. For the 5th value, 5 is also present inside the number of visited list. So we can define that 5 has also been visited, and because of that, we went through all the nodes or all the cities that we were given, and the number of provinces that we were able to make was 2, and which we are going to return as the answer. If we see solution for the time and space solution for this one, Basically the time complexity is going to be big O of V plus E, where V is the number of vertices or number of cities in this case, and E is the number of edges or the connection between the cities that we are given. Pretty simple, and this is pretty standard. Space complexity also going to be big O of V, because the space complexity is based on the visited hash set and the queue that we have to generate, which can hold maximum up to 5 cities for this example. So it is directly related to the number of vertices that is present inside our given example. Awesome. So see how knowing BFS made our life so much easier. Let's move on to the coding explanation for this problem. Let's see the coding solution for the number of provinces problem. This is a really unique problem, and the solution is actually quite simple. First of all, in the main method, we are given the 2 by 2 matrix that defines that what are the number of connected components. Based on that, we would be able to easily identify that what is the total number of edges or total number of nodes present. And once having that, we are going to initialize our visited Boolean array, and initially the number of provinces is going to be 0. Now we are going to run our for loop where we are going to call the BFS method. Inside the BFS method, first of all, we are going to check that whether the current node has been visited or not. If the node has not been visited, we are going to call BFS method to visit all the connected components or all the cities that are connected with each other that form a province. And we are going to increase the number of provinces. So we are going to do provinces plus plus, that was initially set it up as 0. Now let's see that what is going to happen inside our BFS helper method. The answer is quite simple. In the BFS, we are going to initialize our queue, and we are going to have a visited array that to keep track of all the nodes that we have visited so far. For any single input that we are given, we are going to keep on iterating all the neighbors of that particular node that it is currently connected to, and we are going to mark all of them visited. So even when we encounter the same city that has already been processed, we do not reprocess it again because it has already been marked visited. And after this entire process ends, currently in this loop, this provinces variable should have all the answers populated. We can simply add them over here and return provinces as the answer. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs 99.26% faster. So this is pretty fast solution. And don't worry about this. I'm going to paste the solution inside my GitHub, and the link is in the description, so you can check it out from there. Hello friends. So today we are going to learn about depth first search coding pattern, and in my opinion this has to be one of the most popular coding pattern out there, because this coding pattern solves some of the real life problems that many companies or many entire products that are completely built upon, and that is why interviewers love asking this problem. So if you want to ace any technical interview, you are guaranteed to be asked a problem that can be solved using depth first search at one point or the other, and that is why I am asking you to pay extra attention to this problem. The flow of this video is going to be such as that first I am going to talk about the overview of what breadth first search problem is, and in the overview I am going to explain that what type of data structures are being used to solve this problem and how each data structure uses depth first search. Second thing I'm going to talk about it, what is the typical workflow that looks like for a depth first search kind of a problem, and in the end I'm going to show you 3 different real life lead code problems that has been really popular problems and that has been asked in bunch of different big and small companies all across world. So please, I urge you to pay extra attention, because this video is going to be full of so much information that you only need to learn once, and then you would be able to use it forever in your interviews. Let's understand that what does a depth first search is. Depth first search is basically a traversal mechanism. And where does it traverse over? It traverses over trees and graphs. So basically this is depth first search is simple technique to iterate over any given tree or any given graph, and this traversal techniques allows you to solve some of the most popular real life problems such as like going through a maze, or solving like a snakes and ladder problem, or problems such as building path between any two endpoints, and bunch of different ideas. So first let's see that how does DFS is being applied on a tree, and then we will see how it applies on a graph, and then we will try to see that what does a typical workflow looks like. Now you already know that how does a breadth first search works. Breadth first search is typically a notion where we go move out in the breadth before moving out in the next iteration. That is exactly the opposite of what depth first search is. And in the DFS, we go or we pick a branch, we iterate all the possibilities of that branch while keeping track of the nodes that we have iterated over. And when we run out of all the possibilities, we are going to do a backtrack and see if there are any more possible ways where we can iterate over. If there are no possible ways exist, we are going to backtrack again and then move on to the next values in that particular subsequent branch before backtracking to the previous root node again and iterating the same process for the remaining portion of the tree. So that is exactly what we are doing here, where you see that first we iterated in the depth in the left side of the subtree. So we iterated through all of this path. Then we ran out of all the possibilities because there were no children of this node. So we backtracked. There were no nodes that we forgot to cover. Again, we backtracked. We covered this portion. Again, after existing all the possibilities, we again did a backtrack and moved on the right side of the subtree and keep on repeating the same process until we run out of all the nodes, and eventually we would backtrack and come back to the root node. And this is how DFS typically works in a tree. Now for a tree, there are three main methods, and that is in order, pre-order and post-order, that I'm going to talk about next in this video. But this was a general idea or the broader pictorial representation of how a depth first search works in a tree. Let's see how it works in a graph. So this is just a random graph I draw, and even in the graph we can start from any point. So typically in a tree we will usually start from the root node, but that is not the case in the graph. We can start from here, or we can start from here, or any other node. So say for example we start from this node and we go in one direction. So suppose we pick this neighbor, then again we are going to keep track of all the neighbors that we are visiting, and we are keep going until we run out of all the neighbors that exist in that path. Once we run out of all the neighbors, we will do the backtrack, keep coming back, and then eventually we will come back to the same position where we started. Now again we check that have we existed all the possibilities, and the answer is no, because we still have nodes on this path that we haven't visited. So again we will go in depth first search manner, which means we are going in depth to that path as well. And then again, after existing all the possibilities, we will do a backtrack, come back to the neighbor or the root node where we started in the graph. And this would be a typical depth first search flow in any given graph. So after seeing these two things, first question should come to your mind is that why depth first search is different for tree and graph. Why in the tree I mentioned that there are three different ways to iterate over. There is in order traversal, there is pre-order traversal, and there is post-order traversal. Meanwhile in the graph we don't have to worry about any such items, but in the graph we have to worry about something else, and that is called loops, which is not the concern in a tree. So I'm going to explain both of these things right now. So first let's see that what does an in order traversal, pre-order traversal, and post-order traversal looks like for a tree. Again, for the simplicity, I have already drawn an example, and let's see every single traversal one by one. So first we are going to start with a pre-order traversal. Now what does a pre-order traversal means? Now first understand that from any given place we have two possibilities. First possibility is we go either left side or left subtree. Second possibility is either we go on the right subtree. And there is a possibility that when we are going to do some process on the node currently we are at, and that is what this pre-order, in order, and post order, all of these three techniques do, that it allows us to determine that when we are going to process the node we are currently at. So in the pre-order traversal we are going to process the node first. In the in order traversal, first we are going to go in the left, then we are going to process the node, and then we will go in the right. In the post order traversal, first we will go on the left, then we will go on the right, and in the end we are going to process the node we are currently at. So this is what all of these three techniques refer. So first let's see the pre-order traversal in action. So in the pre-order traversal, the flow is going to look like this, that first we are going to visit the node. So first thing is going to be the node. Then we are going to visit its left subtree, and then we are going to visit its right subtree. So the flow is going to look like this, that we are going to start from the root node because that's a given fact. We are going to visit the node. So first item we are going to do any action is going to be on the node number 5. Then we are going to visit the left subtree if there exists, and left subtree exists. So again, this is the entire left subtree. Again, even for the left subtree, we are going to repeat the same process, and the process is that again we are going to visit the node first before visiting its left subtree and the right subtree. So again, the left subtree, currently the next node we are going to visit is going to be the node number 2. Again, for its entire left subtree, it only has one node. So again, we are going to visit node number 1 after that. After visiting node number 1, we are going to do the backtrack, and then for this node number 2 that we have already visited, we haven't visited its entire right subtree. So that we are going to do next, and the next node we would visit is going to be the node number 3. Now what happened is that now after this 4 iterations happen, we have taken care of the entire left subtree from the root, and we already took care of the root node, that was node number 5. So now we are going to take care of the entire right subtree. Again, even for the right subtree, we are again going to apply the logic of node, left and right. So again, this is the node. Currently it does not have anything in the left, but we are going to visit node number 6 first. It does not have anything in the left, so we are going to move in the right. Again, for the right subtree, it has these two elements. So first we are going to take care of value number 8 because node, left and right. And after that, in the end, for this node, we have the node number 7 that we have to take care of. So in the end, the last node we are going to visit is going to be the node number 7. So if we want to see the full traversal is going to look like this. And this is how we are going to move in the pre-order traversal fashion. Now let's see that what would be the in-order traversal looks like. Let me clean this up a bit. So for the in-order traversal, there is a slight difference, and the difference is first we are going to iterate the entire left subtree, then we are going to visit the node, and then we are going to visit the entire right subtree, and we are going to recursively or iteratively keep on repeating the same thing for the entirety of the tree. So we are again going to start traversal from our root, but we will have to visit the entire left subtree before visiting the root node. So in the entire left subtree is going to be this one. But even for this entire left subtree, the same properties applies again. And again, even for this 2, we will have to visit the entire left subtree, and that is going to be the value number 1 only, because 1 does not have any more children. So the first node we are going to visit is going to be the node number 1. And then the next node we are going to visit is that we are going to do a backtrack. And since for this 2, we have visited the entire left subtree, so then we will visit node number 2. And then even for node number 2, we still have elements in the right side of the subtree that we haven't visited. So we are going to do that. The entire right subtree is only comprised of value number 3. So again, we are going to visit node number 3 next, and then we can backtrack. Backtracking from 2, now we have taken care of this entire portion, so we are not worried and we can go back. Now at node number 5, we can say that we have taken care of the entire left subtree for the node number 5. So it is safe to visit node number 5 next. We will visit node number 5. Then again, we are going to repeat the same thing. Now, even for the node number 5, it still has element on the right side of the subtree that we haven't visited. So we are going to repeat the left node right technique again for the entirety of the right subtree for this portion. So for this portion, since for node number 6, it does not have anything in the left side of the portion, we are going to visit the nodes. We are going to visit node number 6. Then again, for these two portions that is present in the right side of the subtree, we are going to repeat the same thing. So before visiting node number 8, since node number 8 has a value number 7 in the left side of the node, we are going to visit node number 7 first before visiting node number 8 in the end. And then we would have taken care of, or we would have visited all the nodes in the in-order traversal. Now, seeing from the solution that we have visited, you should be able to infer a very clear thing right now. And this is actually a solution of a very popular real-life problem. You see that all of these values, they are actually presented in a sorted array. And why they are presented in a sorted array? Because the tree that I draw over here was actually a binary search tree where I'm maintaining a property that every element on the left side of the subtree is going to be less than the root node, and every element on the right side of the subtree is going to be the greater than the root node. And this is present for every single node that has a left element and the right element, that all the values on the left are going to be smaller than the root node and all the values on the right are going to be greater than the root node. And this is how a binary search tree is defined. And using in-order traversal on a binary search tree, we are actually able to generate the sorted array. And see, you just solved a very popular coding problem that is being asked in a bunch of companies. I'm actually going to show you the LeetCode proof that this question exists, and you already know how to solve it. All you need to do is do in-order traversal on a binary search tree to find the sorted result. But now let's just go back to our technique. And now let's see that what does the post order traversal mean. And let me again clean everything up and I'll show you the post order traversal as well. Now in the post order traversal, first we are going to visit the entire left subtree for any root node. Then we are going to visit entire right subtree, and in the end we are going to visit the node. So for the 5, what we are going to do is first we are going to visit entire thing on the left subtree. Then we will visit everything in the right subtree. Then in the end we will visit this node number 5, and we are going to iteratively or recursively keep on repeating the same process. So first let's see what would happen for this node number 5. We start at 5. It has elements on the left subtree that we haven't visited, so we go on the left subtree. Again, even for this 2, it has elements on the left subtree that we haven't visited, and that is value number 1. Now for this value number 1, it does not have any more left or right children, which means we are sufficiently able to visit this node. So first node we are going to visit is going to be node number 1. Then we are going to backtrack to its previous node, that was going to be node number 2. Again, even before visiting node number 2, we will have to visit the entire right subtree for that node. So we are just going to do that, and that is going to be node number 3. So then we are going, after visiting node 1 and node 3, we would be able to visit node number 2. After visiting node 2, we will again backtrack to node number 5, stating that now for this node number 5, the entire left subtree has been taken care of, but it still has elements on the right subtree that we haven't taken care of, that we are going to work upon right now. So even for the right subtree, we are going to apply the same logic. So for this node number 6, since it does not has any nodes on the left, it still has nodes on the right that we haven't taken care of. So again, we are going to visit the right subtree for node number 6. So that is going to be node number 8. Even for node number 8, it still has elements on the left that we haven't taken care of, that is node number 7. So next value after visiting this node number 2 is going to be node number 7. After 7, we are going to visit node number 8. After visiting node number 8, we are going to go backtrack and visit node number 6. And in the end, we are going to visit node number 5. So what we did in this post order traversal is that we took care of all the elements that were present at the leaf before moving back to its like predecessor, and this would be the post order traversal for this tree. Now after learning in order, pre-order and post order traversal, the first question that should click your mind is that why this is only limited for trees. Meanwhile, the DFS method that you already know can be applied to trees and also graphs. Then why it is only limited to trees, where we need to do like this in order, pre-order and post order traversal, meanwhile nothing for the graphs? And the reason is quite simple. The reason is that for a graph, we are actually able to start at any single position and start iterating in the DFS fashion. Meanwhile, for a tree, we are limited to start at the beginning. And when we start at the beginning, we have a couple of possible ways to iterate over that. Either we are keep on going into the left direction before moving on to the right direction, or we are going to mark the node first before moving the nodes again. And that is why this in, pre and post method is in action and for the trees. Meanwhile, there is no such concern for the graphs. But I told you that for the graphs, you will have to take care of one more thing, and that is loops. So now let's see that why for the graphs you will have to take care of the loops and not for the trees. Okay, so for this graph, let's try to move in the DFS fashion, and we can start from iterating from any single node. So let's just say, for an example, we will start iterating from this node number 1. Now from this node number 1, who are the neighbors of node number 1? first neighbor is 8 and second neighbor is 2. We can pick any branch and keep on moving in that direction, depth first search manner. So say for an example, we start move in this direction. So first we visited node number 1, then we visit node number 2, then again we keep on repeating the same thing. So even for node number 2, it has 2 neighbors. First one is node number 3 and second is node number 4. So let's just say if we visit node number 3 as the neighbor, and next we visit node number 4. After visiting node number 4, again we have still 2 possibilities. Either we can visit node number 5 or we can visit node number 2, because both are neighbors of 2, so we still have 2 possibilities. Say after visiting this node from 4, we decide to move back on the node number 2. What would happen now is that from this 4 we would visit node number 2. Again from this node number 2 we would again visit node number 3. Again we would visit node number 4. Again we would visit node number 2. So see, we are stuck in a cycle, and because we are stuck in a cycle, we need to take care of that all the nodes that we have previously visited. If we don't know that what are the nodes we have already visited, and we keep on repeating this DFS coding technique on the graph, we could end up in a cycle, and this is going to keep on running infinitely. So this is a huge problem that we have to take care of, and this problem can be solved pretty easily by keeping track of either a visited array or a visited hash set. So you have 2 options to use. You can use a visited array or a hash set. Okay, I typically like to use hash set, but in many solutions you can also use an array as well. Both are going to incur the same kind of space complexity because you are using an additional data structure, but this is solving a very popular real life problem that is going to save you so much computational power. So say for an example, in this problem, we decide to initialize a visited hash set, that every single node that we have visited so far, we are going to mark it as visited before moving to the next element, and we would only move in the direction for the nodes that we have not visited. So applying this logic, again we start from this node number first. Node number first currently, okay, we say we have visited node number first. Okay, let's just mark it as visited. We move in the direction, we visit node number 2. Node number 2 has not been visited, so we can go in that direction. And again, let me plot the path on over here as well. So from 1 we move to node number 2. Again from node number 2 we have the possibility to move to node number 3. 3 has not been visited, we are going to mark 3 as visited. Okay, marking node number 3. Again going to the node number 4, marking node number 4 here, and node number 4 as visited. Now again from this node number 4 we have 2 possibilities. We can go to node number 5 or we can go back to node number 2. But when we try to go back to node number 2, we can clearly see that 2 has been visited. Since 2 has been visited, there is no point in going back to this node number 2, and the only direction we can go back to is going to be node number 5. So next we are going to visit node number 5. After visiting node number 5, we are going to go back to node number 6, and then we are going to go back to node number 7. And this is going to be like the one of the iteration or one of the path we took starting from node number 1. Then we are going to do backtrack, and we are going to see that are there any other neighbors that we have missed that has not been visited, and that is not such a case for this one. So eventually after backing track or after doing like a backtrack, we would end up at node number 1. Again from this node number 1 we haven't visited this neighbor, so we will go in that direction. So we will go to node number 8. 8 has not been visited, we'll mark 8 as visited, and then 9 as visited. And then after visiting node number 7, we are going to visit node number 8 and node number 9. And this is going to be one of the DFS traversals starting from node number 1, where we eliminated the need for loops and we were able to iterate in a very smooth fashion in the DFS manner. So this is the whole logic, that why for trees you will have to use in order, pre-order and post-order traversal. Meanwhile for the graphs you will have to take care of loops using either visited array or a visited hash set. You can pick and choose, but you have to remember that you will have to use it. Now let's see that what are different ways to iterate over in the depth first search, and there are 2 ways you can do it. You can do it recursively or you can do it iteratively. I'm going to show you both the ways before moving on to 3 solutions. Okay. Now, when it comes to DFS, there are actually 2 ways to implement DFS. First one is a recursive way using recursion, and second one is an iterative way. So first I'm going to show you that how does recursion works on a DFS and what is a typical flow of using recursion looks like for a tree and also for a graph. I'm going to show you both the examples. Now, before understanding and diving deep into the DFS, first you need to understand that how does a typical recursion works. Now, if you don't know what recursion is or how recursive functions behave, I encourage you to first go ahead and study recursion. Now, in this example, we have a binary tree, and for this binary tree, we will try to do the in order traversal for this binary tree. Now, again, in order traversal means left, node, and then right. This is the logic we are going to apply. So initially we are located at this first position. Now let me show you how the recursion is going to work for this tree using this root node example. Currently for this root node, we are going to apply the logic of left, node, and right. So first for this node, we will check that whether does it has left child or left subtree. Yes, it does has left subtree entirely. Now even for this left subtree, again we will have to apply the same logic of left, node, and right. So in this case, whatever we were implementing for this node or for this root node, now we are going to treat this node number 2 as our root node, stating that even for this entire subtree, if this was a tree on its own, again if we had to use in order traversal, we would use this logic on left, node, and right. And that way we are going to, again for this root node, try to see that does it has a left child, and yes, it does have a left child, that is node number 1, but this node number 1 does not have any children of its own. So this is going to be our terminating case where we will get out of the recursion, because we cannot go anywhere further, and we can actually node this, we can actually treat this node as being like a process. So we are now at this position for this particular one, and this is how recursion is going to end for this portion at this particular node, that we are done with it. So first node we are going to visit is going to be node number 1. Again, now we are going to do the backtrack, and after backtracking, even for this true, again we are going to apply the same logic, that left we have already taken care of, but node we haven't taken care of. So now we will mark node, because we visited all the left subchilds possible for this root node. But even for this root node, it still has a right subchild, and again if this right subchild, say for an example it had additional children, we would have again used this left node right logic. But since it does not have any additional children, we are going to treat this as a terminating case for recursion, and then the next node we are going to visit is going to be node 3. After visiting this, now we have taken care of all of these 3 nodes, and now we will go back to our root node. Again, we took care of the entire left subtree for this root node. So now we are going to mark 4 as visited as well, that we already took care of it, but we are yet to take care of the right side of the subtree. Again, rather than treating as a right subtree, we can treat this as a subtree or as a tree on its own, where we are applying the DFS. And again, for this node number 5, we are going to visit the left child or left subtree first. But since it does not have any left subtree, we are going to visit node number 5 itself, because we are visiting the node. After visiting node number 5, we will have to apply the same logic for the right subtree. And again, for the right subtree, we will have to visit node number 7 and node number 6. But again, from node number 7, we have a left child, which is node number 6. So we are going to visit node number 6 first, before backtracking and visiting node number 7. And since 7 does not have any right child, we are able to go back, and now we have visited the entire tree on its own, and we are done with the recursion. Now every single time whenever we meet this condition, or whenever we have been able to mark the nodes, then we would call the we would backtrack and come back again until we are done with every single node inside the given tree. And every single time we are iterating over a new set of subtree, we are going to call our recursive function to implement the depth first search logic again. And this is how recursion would work on a tree. Let's see how the logic is going to change or remain the same for a graph structure as well. Now, even for a graph, again, the logic is going to remain same. We are going to have our recursive function. We are also going to have some terminating condition, that how when we define that the node has been completely visited and we can move forward. And again, in the graph, since we are applying the depth first search, we are going to keep on going in one branch before going in the other branch. So say for an example, in this graph, we start iterating from node number 3, because in the graph we have the flexibility to go in any particular direction. Now every single element in a graph has two items. It has a vertices and it has an edges, and depending on the vertices and edges combination, every single vertices has one or more than one neighbors, and we are going to visit every single neighbor. Now you already know that for a graph we will have to take care of all the nodes we have visited, otherwise we would end up in a infinite loop. So we are going to have a visited hash set that is going to be much of a help to us, and using this visited hash set we would be able to create a terminating condition for our recursive function. So let's just start iterating from node number 3. Now currently first neighbor we are going to visit for node number 3 is going to be node number 6. Currently node number 6 is not visited, we are going to mark it as visited. Again for node number 6 we are going to call the same recursive function that is going to call the neighbors of node number 6. Now since node number 6 does not have any neighbors, the only neighbor it has is node number 3, but since node number 3 is where we started visiting, so let's just mark node number 3 as currently visiting as well. Okay, and now we are not going to go back to node number 3, so now we are going to mark node number 6 as visited. And after that, so this is going to be the terminating condition for a node to be considered as visited, that if we have taken care of every single neighbor for that particular node. So for node number 6 we are done, we are going to do our backtrack, and from node number 3 again we are going to move to the next neighbors that is not node number 6. This is the key part, that is not node number 6, because we already mark it as visited. Again for node number 3, let's just say we go in the direction of node number 4, so we mark node number 4 as visited. Now again for the node number 4 we are going to apply the same logic and treat that as if the graph is starting its traversal from node number 4, because we are using our recursive function to call the next subsequent nodes. And for node number 4, okay, node number 3 we cannot go to, node number 5 we can. So again mark 5 as visited, again from 5 go to node number 2, again from node 2 go to node number 1. So okay, 5 2 1, and again from node number 1 eventually we will come back to node number 3. And since there are no other nodes left, we are going to be done with every single element. Now again for this case, now at node number 3's position, since we took care of every single neighbor of node number 3, we are going to consider node number 3 as done and the completion of DFS, because all the nodes that were present where we were able to visit them in a single go, and they are all mentioned in the visited hash set. If we want, we could have plotted on our graph as well, that after visiting node number 6 we would come back to node number 3, then we would go to 4 and then 5 and then 2 and then 1 and again come back to 3, but we are not going to do that. So this would be like a traversal path. It could also be possible that there is one more node number 7 over here that is not connected with any edge, and there could be possible that there is also one more node number 7 and 8 that is not connected with any edge. So again for this one, after traversing all of these values, still we are going to use recursion to go over these two nodes, and we are going to add them to our visited hash set, and then we are going to add them to our nodes that we have processed in some way, shape or the other form. And this is how recursion would work typically for graph and tree data structure. There is only one difference between recursion and iteration, but in order to understand, first we will have to understand that how does an iterative DFS works. So let's just see an example that how does a iterative DFS work. Now again for the iterative procedure, I'm going to show an example for a tree and also for a graph, but I'm going to explain you very quickly. And the way iteration is going to work is that we are actually going to use stacks in order to implement our DFS function. Now we all know that what is the property of a stack. A simple property of a stack is that last in first out. LIFO is the property, and that is what we are going to use at the most. We are going to create a stack, and inside the stack we are going to add our root node, and again we are doing the in order traversal. Okay, so left root node. So first we are going to add node number 1 over here. Okay, now after adding node number 1, we are going to see that does it has a left child. Yes, it does has left child. So who is the left child? Left child is node number 2. Again for node number 2, does it has left child? Yes, it does, the node number 4. So we are going to mark node number 4 over here. Again for node number 4, does it has a left child? No, because it does not have a left child, which means now we will have to process node number 4. So we are going to pop node number 4 out. After popping node number 4 out, currently the first node we are going to visit is going to be node number 4. Now after popping node number 4 out, again for node number 2, it does not have a left child that we haven't taken care of, so we are going to add the node number 2 next. Then again for node number 2, we haven't taken care of node number 5. So after popping node number 4 and 2, we are going to push node number 5. Again for node number 5, it does not have any more children, so we are again going to pop node number 5 next. After popping node number 5, we are going to backtrack. So we already took care of all of these three. Now we are at node number 1 position. We are going to pop node number 1 out because we are doing in order traversal. But after popping node number 1 out, it still has right child that we haven't taken care of. So we are going to push node number 3 again. And even for this node number 3, it does not have a left child. So we have been able to pop the node number 3 out. After popping node number 3 out, we still haven't taken care of the right child, right children or right subtree. So again for node, we are going to push node number 6. After pushing node number 6, we are going to check that whether node number 6 has any left child or not. Yes, it does. So because there is a left child, we will have to do a push operation. So we are going to push node number 7. Node number 7 does not have any more children, so that is a terminating case. So we are going to pop node number 7 out. And after popping node number 7, we would be able to pop node number 6, and then we would be done with our iteration. And this is how in order traversal is going to work using a iterative method for depth first search. Basically we are using stack to keep track of the nodes that we already entered, and that is going to allow us to implement our backtrack much efficiently, and we would be able to solve this problem. Let's just do the same thing with a graph. Now this looks like a tree, but this is actually a graph because there exists a loop inside this. Typically trees does not have a loop, but graphs do. So that is why this is a graph. Again, let's just implement our iterative method. We are going to use stack. We are going to use the property of last in first out. And in our stack, again, we are also going to have a visited hash set because this is tree. So we will definitely need this. Say for an example, we start traversing from node number 4, node number 2. We put node number 2 in the end. Now who are the neighbors of node number 2? So first neighbor is node number 4. Okay, now who are the neighbors of node number 4? None, because node number 4 does not have any neighbors that we have. And also we are going to mark 2 and 4 as visited. Now because there are no other nodes that are visited, that are not visited, and they are neighbors of 4, then we are going to do a pop operation. So first node we are going to pop out is going to be node number 4. After node number 4, we are again back at node number 2. Still it has neighbors that we haven't visited. So let's just say we visit node number 1. We mark 1 as visited. We add entry 1 over here. Again, 1 has neighbor 3 that we haven't visited. So 1 and 3 comes into the stack and visited hash set. Again, 3 has node 6 that we haven't visited. So 6 comes here. Again, 6 has 7 that we haven't visited. So 7 also comes in the stack and also in the visited hash set. Now from 7, it does not have any more that we cannot visit. So now we are going to pop 7 out. So after 4, we can say that, okay, let's just say 7 has been popped out. Now again, we are at this junction 6. For this junction 6, we haven't taken care of node number 5, and that hasn't been visited. So we are going to mark node number 5 over here as well. And from this node number 4, now every single neighbor of this node number 5 has been visited. So now we can simply do our pop operation. So first node number 5 is going to pop out, then node number 6 is going to pop out, and every single element is going to keep on popping out in the recursive fashion. So then 3, 1 and 2 are going to pop out, and this would be like one of the traversals. And everything we did not use recursion, we used the iterative method using stacks. So this is a key point to remember. Whenever you have to implement stack with an iteration, then whenever you have to use DFS iteratively, you must use stack, because this is the golden rule. And every single interviewer, if you show them recursive solution, they are going to ask you that, hey, can you do it iteratively? If you show them iterative solution, they are going to ask you to do it recursively. So it's good to know both the methods. And now let's just see some examples. So the first example we are going to see is going to be maximum depth of a binary tree. And this has been really popular problem amongst many top tier companies such as Apple, Google, Amazon, LinkedIn, Spotify, Microsoft, Facebook, Bloomberg, Yahoo, Uber. They have all asked this question. So this is a really popular question. And let's see the problem statement. Also, this is a very well like problem and a lead code easy problem. Problem statement is quite simple. We are given the root of a binary tree and we need to return its maximum depth, which means suppose this is the example we are given. We know that the maximum depth for this one is going to be in this direction or in this direction. In either cases, the answer is going to be 3 because we are seeing 3 nodes in depth. So this is what we need to return. So the logic is going to be quite simple. We would be able to solve this problem using DFS quite easily. Now, since this is tree, we have 3 options to use: in order, pre-order, or post-order traversal. We can use either one of them. I like using in order, so let me just show you the solution using in order. And for this problem, I'm going to show you the solution using iterative method. So I'm going to show you the solution with the stacks. So first, let me quickly initialize a stack that I'm going to use to iteratively traverse over this given tree. Also, we need to calculate the depth. So we are going to have a variable called depth, and I'm just marking it as DEP. And initially the value is going to be 1 because we are guaranteed to have a root node, and the root node by itself is going to have depth 1. So we already start with this one. Okay, now we are going to apply a simple logic that whenever we reach to a leaf node, whenever we move to the next element and we reach to the leaf node, this is the last element that we can visit in this path, nothing more than that. So up until this point, whenever we are going downwards, we are going to increase the count for our depth. But since this is DFS, we will have to do backtrack many times. And whenever we will have to do the backtrack, we are going to subtract the depth we have been able to find so far. And we are also going to have a variable called maximum depth that is going to allow us to capture the maximum depth we have been able to capture, because it could lie anywhere on the graph, so on the tree. So let's see the solution in action. Okay, first we already know depth is 1. Now from this portion we start the in order traversal. So we are going to do left node and right subtree logic. So we are going to go in the left direction since we went down, and again initially the first value is 1. Now next value we are putting in is going to be node number 2. Since we are going down in the depth or we are adding value to the stack, in either case we are going down in the depth. So we are going to increment our depth. So currently now the depth is going to become 2. And so far the maximum depth we have been able to find is also going to be 2. Now again from this 2 since it does have a left node, we are going to again add entries to our stack. So we are going to increment the depth, and also the maximum depth we have been able to find so far is going to be value number 3. Again, now from this 4 we cannot go down any further. So now we will have to pop 4 out. The moment we pop 4 out, now we are going to go do a backtrack. So because we are doing a backtrack, we are going to subtract the value of the maximum depth we have been able to find to 2. Not maximum depth, but the depth we have been able to find to 2. Now the maximum depth is going to remain 3 because that is the maximum value we have found so far. Again from 2, we are going to add value number 5 inside our stack. Since we are adding value, we are going to increment the value of our depth to value number 3. The maximum depth is going to remain same. Again we are doing backtrack once and backtrack twice because we are going to get rid of both of these elements. So we are now again at position number 1. Now position number 1 we are also being able to pop out because currently we are visiting the node, but it still does have right children that we haven't visited, and same with this one, the depth is going to change to 0 when we are at this portion. We already popped this one out as well. Now for this node number 3 we are going to put it in. So again depth is going to change. Now depth is going to be 1. Again for this 3 does not have any left children. So again we are going to process this node number 3, but we are going to keep depth as 1 because 3 is already located at depth 1, because 3 still has right children that we haven't visited. Now we are going to push to node number 6 in. So again depth is going to increase and depth is now going to be 3. And also from this then again we are going to have one more value 7 inside our graph. So we are going to have depth as 4. Since depth is maximum right now, we are going to increase the max depth as well. And after visiting this node number 7, we would be able to get rid of node number 7 and also node number 6. And now we have visited every single node inside the tree. So the maximum depth we have been able to find is going to be 4. And this is what we are going to return as the answer. So this is going to be the whole solution for this problem. And I know this was a LeetCode easy problem and very justifiably. And I like this problem because it opens your mind about the depth first search concepts, and you would be able to solve it quite easily. Now let's see the coding solution for maximum depth of binary tree. So first of all, we are going to initialize a linked list called stack and also a linked list called depth. Then we are going to check for the edge case that if the given root is equal to null, we are going to return 0 immediately. If that is not the case, we are going to add the first value to our root, and we are also going to add that value to our depth linked list, stating that this is the node we are currently at. Now we are going to have two variables called depth and the current depth, and this is to keep track of the maximum depth we have been able to find so far. Now we are first of all going to iterate until the given stack is empty. Now first thing we are going to do is we are going to mark the root node as the last value we pull from the stack. Then we are going to add the current depth as the depth of poll last for this in this particular linked list. And then we are going to check that if the given root is not equal to null, in that case we are first going to calculate the depth, which is the maximum value we have been able to find, that whether the current depth is the maximum depth or not. And then we are going to add the left child, we are going to add the right child. Because we are adding two entries, we are going to add two more entries to our current depth at any given current location. So we are going to mark value by +1. And in the end, after this whole process is done, we only need to return this variable depth that contains the maximum depth we have been able to find. So let's try to run this code. And seems like our solution is working as expected. Let's submit this code. And our code runs decently efficiently in terms of space complexity and very efficiently in terms of space complexity. So I would be posting this in my GitHub repository. The description is mentioned in the comments, so you can check it out from there. The LeetCode problem we are going to solve is going to be path sum problem, and this is a very now the LeetCode problem we are going to solve is called path sum LeetCode problem, and this is a really popular problem asked at some of the top companies like Amazon, Microsoft, Google, Facebook, Bloomberg, Apple, Walmart, and Adobe. So I'm paying my utmost attention. So again, this is a LeetCode easy problem and also very well liked problem. If we see the problem statement, it's quite simple, that we are given the root of a binary tree and we are also given an integer called target sum. Now we need to return true if the tree has a root to leaf path that sums up to the target sum, which means suppose this is the input we are given and we are given the target sum is equal to 9. Then in this case, we can see that if we do the sum of these three elements, so this is the root node, this is the leaf node, and if we do sum of this path, then the sum is going to be 9. So in this case, we are going to return true. But suppose in this case, we were given the target to be, let's just say any arbitrary value like 11. In this case, since there is no path that sums up to value 11, we would have written false. So this is the whole ask of the problem, and the solution is quite simple. We would be able to solve this problem using depth first search method. Now suppose this is the input we are given and we need to check that whether the target sum is equal to 8 possible or not. So the solution is going to be quite simple. Let's just do in order traversal. Now we are going to do this recursively, iteratively, whatever you want to do. Let's just do iteratively. Okay, so we are going to use a stack. Now we are also going to use this function called sum of the path that we have been able to find so far, and initial value of the sum is going to be 0. The first value we pop inside the stack is going to be node number 1. Now again, for this node number 1, we are going to increment the sum. Sum is going to be currently at 1. Now we are moving along this path 1 to 2. So again, from 1 to 2, again we will have to add entry 2 over here. Again, sum is going to be 2, so 1 to 2 is going to be value number 3. Now again, from value number 3, from this position 2, we are going to move to this direction. So now we are going to add one more entry into our stack, and that is entry number 4. So now 3 and 4, the sum is going to be 7. Again, it is not the target value of 8. Now currently we only need to consider the path sum from root to leaf. Now you notice that the sum that I have created so far, initially I was only doing the sum between these two entries. Even if that would have met the target value, we could not still consider it to be the path sum. So the question is that how do we know that the element is a leaf element? We only know it that if the element does not have a child. So the moment, even if we find the correct sum as the target sum, we will have to check that the last element we included, did it have any more children or not. If it does have children, then we would not consider it to be a successful scenario. I understand that my explanation makes sense to you. So now currently this target sum is 7. Now since at this 4 we cannot go down further, but we still have elements that we haven't visited. So say for an example, if that is the case, we are going to do a backtrack. So we are going to get rid of 4. The moment we do a pop operation from our stack, we will also have to reduce the sum as well. And now the current sum is going to be 4 at the sorry, not 4, the current sum is going to be 3 at the moment. Now at this sum 3, again from this 2, now this time we are doing a post order traversal. So we are doing left, right, and then node. Yeah, I know initially I said in order, but that was my mistake. We would be able to do post order in this one. And now we are going to visit the right node for again. Now this right node, the value is 5. Because we input 5, we are going to mark it as sum. So sum is going to be 3 plus 5, so sum is going to be 8. Now this sum matches this target value. So we will have to check that whether this 5 is a leaf node or not. And we can check it quite simply, because this 5 does not have any more children of its own. We can mark this node 5 as leaf node, which means this sum equation makes sense and we would be able to return true in this case. Now using depth first search, you are able to solve this problem quite beautifully and quite efficiently. And if we see time complexity, the time complexity is directly in correlation with the number of nodes that are present. So we can mark it as big O of n, because for DFS we don't need to do anything else. In terms of space complexity, because we are using an additional stack, we will have to mark it as space complexity. But in the stack, at any given position, we are going to have all the elements that are at max the depth of a binary tree. So it is going to be in big O of log n fashion, nothing, not the big O of n. And if you say that this is log n, your interviewer is going to be really impressed, because he thinks that you have really good knowledge of data structure and algorithm, which is true and which is awesome. Now let's see the coding solution for path sum problem. Now in the path sum problem, again we are going to move iteratively, and we are going to initialize a node stack called linked list, and we are also going to initialize a linked list called sum stack that is going to keep track of the current sum we are at. Now initially we are going to add the root value to our node stack that we have created, and then we are going to add the value to our sum stack. So sum is going to be sum minus root value, because we are adding the value inside our root node. Now we are going to have a tree node to iterate over the different tree nodes, and we are also going to have keep track of the current sum. Now again, for the iterative method, the method is quite simple, that until the given stack is not empty, we are going to keep running inside the loop. Now in the loop, first thing we are going to do is we are going to poll the last element that is present inside the stack. Because we poll the element, and we are also going to mark the current sum to whatever the sum we have been able to find for the last poll stack element. Now we are going to run a condition that if the given right node is equal to null and left node is equal to null, which means that both the nodes are at the correct position and current sum is equal to 0, which means that the current sum is the target sum. Then in that case we are going to return true if that is not the case. And if right node is not equal to null, we are going to deep dive into the right node and we are going to add the current sum we are at. If that is not the case, and if it has a left node, again we are going to repeat the same thing, and we are going to subtract the sum from the current sum, because current sum is the total number of sum that we need to return. And in the end, if we haven't returned true but in this loop, which means that the target sum is not being able to meet up between the root node and the leaf node, so in that case we are going to return false in the end. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code, and our code runs decently efficiently in terms of time and space complexity. Again, I'm going to post the solution of this code in my GitHub, so you would be able to check it from there. Now let's see a really popular LeetCode problem called core schedule, and this is a LeetCode problem 207. This has to be one of the most asked graph and tree kind of a problem. It has been asked in all kinds of companies such as Google, Amazon, TikTok, Microsoft, Facebook, Apple, Uber, ByteDance, and then Bloomberg, Snapchat, and bunch of different more. So this problem has been really popular. Let's see the problem statement. Basically, this is a LeetCode medium problem, very well like problem. Now in the problem statement, we are given an integer value called number of courses. Suppose we are given the integer value of number of courses is equal to 5, which means that we are given that there are 5 courses, 0, 1, 2, 3, 4. These are going to be 5 different courses that we will have to schedule for. Now we are also given one more thing, and that is that we are given the prerequisites for any single course. And this prerequisites is a really common thing, because even in real life we all have been to universities, and if you want to do, say for an example, comp 202 course, then it must have a prerequisite of comp 101, that if you haven't completed comp 101 you cannot get admitted into comp 202. So this is just an example of what a prerequisite is. Now in this case, we are given an array of prerequisite where every single tuple is a value such as A and B, which means that in order to complete course B, we must first have taken course A. So suppose we are given that in this case, we are given 5 courses, 0, 1, 2, 3, 4, 5. And if we are given a value such as like 0, 1, which means we can determine that in order to complete course 0, we must have completed course 1 first before moving forward. So using this logic, we would be able to use this as to create an edge between any two nodes, and we are going to treat number of courses as nodes. So now we have both the values we needed. We have a node and we have an edge, which means we can create a graph based on the given input. So suppose again we are given 5 different courses, and say these are the dependencies, right? That 0, 1, 2, and then 3, and then 4. So these are the 5 courses that we are given, and these are all the dependencies we are given. So quick question, are we able to complete all the courses in this problem? Of course we can. Why? Because first we are going to complete course 0. In order to complete course 0, we will have to complete course 1. In order to complete course 1, we will have to complete course 2. Course 2 we can complete because it does not has any prerequisites. So after completing course 2, we would be able to complete course 1, and then we would be able to complete course 0, which means we would be able to solve our this dependency quite easily. Same goes for this one, that we can complete course 4 because there are no prerequisites needed for course 4, and then we can complete course number 3. So in this case we can return true because all the courses can be scheduled. But suppose we are given a scenario like this, that again we are given the same set of conditions, but we are just given a tricky scenario where in order to complete this course number 2, say we will have to complete this course number 0. In this case, now will we be able to schedule all the courses or take all the courses? The answer is no. Why? Because these courses we can still complete by completing course number 4 and course number 3. But now in order to complete course number 0, we will have to complete course number 1. In order to complete course number 1, we will have to complete course number 2. In order to complete course number 2, we will have to complete course number 0. So we are running inside a cycle, and we would never be able to get out of it. And that is the whole crux of the problem. So the problem simply becomes that we take the number of courses that we are given, we treat them as nodes, the prerequisites we treat them as an edge, and then we create a graph. After creating a graph, all we need to do is run a DFS. We can do it recursively, iteratively, it's up to us. And after using this DFS, all we need to do is to check that whether there exists a cycle or not. And how can we check that there exists a cycle or not? Using visited array or visited hash set. And this is why a lot of companies love asking this question, because see how many different topics it covers in a single problem. That is a real life use case that is pretty popular in many universities. So that is why a lot of companies like to ask this kind of question. Let me quickly show you the solution, and I urge you to think hard and deep on this problem and try to solve it on your own. But I'm just going to show you a quick implementation of the solution. So suppose again, let me just go back to my previous scenario. Suppose these are all the prerequisites and graphs we are given. So now we will try to see that whether there exists a cycle or not, which means we are going to run a DFS simply. Now this is a directed graph, which means if there exists an edge between node 0 to 1, it is not necessary that there has to exist an edge between 1 to 0 as well. Now we are going to first initialize our visited hash set. We are also doing this iteratively, so we are going to initialize our stack for our DFS. We are opening both the buckets. Suppose we start iterating from 0. Now from node number 0, in order to complete node number 0, we will have to complete node number 1. So first let's just mark node number 0 over here, and we are going to say that okay, node number 1 is a neighbor of node number 0. So since 0 has a neighbor currently, okay, we mark 0 as visited. Now 0 has a neighbor 1, so we are going to add 1 to our stack. Again 1 has a neighbor 2, so we are going to add 2 to our stack, and at the same time we are going to mark them as visited. Now 2 does not have any neighbors, which means we can pop 2 out. After popping 2 out, we would be able to pop 1 out. After popping 1 out, we would be able to pop 0 out, which means we took care of this entire path and we found no issues, and currently we have been able to visit this node 0, 1 and 2 in our visited hash set. But we know that we are given 5 courses, and currently so far we have only visited 3 courses. So since there are 2 more courses that we have to visit, so let's just start by visiting course number 4. Now course number 4 does not have any neighbors, which means we won't be able to do much with it. But for course number 3, it does have neighbors. So currently let's just start with course number 3. So course number 3 currently has and we are going to mark 3 as visited. 3 has a neighbor 4, we are going to mark 4 as visited. And in the end, since we visited all 5 nodes, we found no issues, which means we can return true that we did not find any cycles. So by implementing the graph function, we can say that all the courses can be scheduled. Now suppose there exists a cycle. So suppose even in this case, from this 3 to 4, there was a cycle. So again 4 has a value that points to 3. So again 4 is calling a neighbor 3. So we will try to put 4 into the stack, and we would try to add entry number 3 over here. But we would say, hey, 3 has already been visited. So since visited node cannot be visited again, so we are going to say that cycle exists, and we would be able to return false in this case. And this is the whole solution. If we see time complexity is going to be big O of v plus e, where v is the number of vertices, e is the number of edges. So v plus e is pretty standard for any graph kind of a problem. Space complexity is going to be directly correlated with because of these 2 items. So it is going to be big O of v, or big O of number of vertices. And this is a really popular problem, and it has been liked by all people all across world. So that is why I ask you to solve this problem on your own, because it is going to be really helpful for your next interview. Let's see the coding solution for course schedule problem. Now in the course schedule problem, we are not given by default the structure that looks like a graph. So first of all, we are going to create a hash map where we are going to keep an integer as a key and the list of integers as the value, and we are going to name it as course dictionary. Now we are first of all going to build up a graph structure that we will be able to iterate, where depending on any given course, we would have its dependencies listed inside the hash map, and the hash map is going to allow us iteratively allow us to do all the procedure quite smoothly, because we would be able to fetch all the data in big O of one time. Now after creating the graph like structure, we are going to have 2 variables. First one is called checked, so this is going to be our visited array, and second one is the path. This is the number of courses that are currently present in the path or not. Now we are going to run a for loop, and in a for loop we are going to go over every single course until we reach out of them, and we are going to check that whether from the current course are we able to create a cycle or not, and we are going to give as an input all the checked courses that we have gone through and all the paths that we have gone through, and this is going to be a helper method. So let's see the is cyclic helper method. Now in this helper method, first of all, we are going to get our hash maps, all the graph and all the data. First thing we are going to do is to check that whether the given node, if that has been checked or not. If that is checked, which means that there is no cycle and we can return false. If we are also going to check that are we going through the previously visited node. If that is the case, which means we identified a cycle, and we are going to return true immediately. Now if both are not the cases, we are going to check that if the current course dictionary contains the course that we are currently at, which means there is no loop, so we are going to return false. If that is not the case, we are going to mark that the current course we are at that has already been in our path, and we are going to have a boolean variable set to false. Now again we are going to run a for loop for every single child of the current course, and we are going to again recursively call this method again and again and again, and at any moment we identify that this return variable is not false, we are going to is false, we are going, and at any moment we identify that this return variable is true, that means we are going to break out of the loop, and we are going to mark that the current path is mentioned as false, and we are going to say that the current course we have already returned as true. In the end, we are going to return this ret boolean variable that we set up. Now let's try to run this code. Okay, solution is working as expected. Let's submit this code, and our code runs pretty efficiently compared to in terms of space and time complexity. And I will be posting the solution of this code in my GitHub, and the description of the GitHub link is present in the description of this video, so you can check it out from there.